This is the direction, the next talk, and actually,
So you did have people who didn't want to travel into the US because of issues.
that has said, you know, pretty adamant about the fact that, you know, most women.
There was even an American.
Yeah. Listen, you know,
She was like, passing here, she's a postdoc in Europe, and apparently her advisor was like, yeah, don't go.
Yeah.
Yeah.
I think it's going to be great, so. And listen, it's fine.
So I'm going to be able to get critical to go down and get the top grade.
Yes, yeah, I just exchanged an email with him yesterday. Yes, I'm glad that he would be giving a talk. Yeah, right.
Oh, he was on the Slack an hour ago. He had the time zone wrong. I was like, wait an hour.
Yes, and yeah, he also contributed 22. I don't remember if 22 was there at McDonald's, but anyway,
It's trying to be sick. Yeah, soon. Soon. Yeah, a couple of minutes.
like I have it here, that I clashes with, and eventually over the years, you know, it's fine. Yeah, yeah, I think, yeah. And is much.
I can't do anything.
Sometimes driving friendly, you know, fights, but yeah, that's right.
I feel and this is one of the things sort of full of
That is true. This is why I remember this conference I did last year in '99 maybe. So I was completely unaware that my advisor has this fight back on birthday. Anyway, it's a this older guy, you know, inches taller than me, inches wider in each direction. Lashing at me, I'm saying, this guy just said, you know, like I said, I talk tomorrow, you know, and he didn't. So, you know, so I felt like I stood my ground, but I wasn't, you know, word got back. So is it like 25 already? Because I think that, you know, or whatever. Is it?
Yeah.
So maybe, yes, I'll just give another minute for whoever is here to get settled, but then I think we'll get started. And I think we'll, let's see, checking the time.
Oh, hi, David.
Hello, how are you?
Okay.
It looks like you didn't make it to Alabama either.
That's right.
Hello, David. Yes, I see. Okay. Well, welcome. Yes.
Thank you.
Yes. Can you see me, by the way? I mean, not that it's a big deal to see me or not, but can you hear me?
We can hear and see you. I can hear and see you.
Yeah, it should be all set.
Yes. We're gonna get started in a minute. Well, we said 8:25, so maybe we should give another minute for people here in the room. But I guess you from Zoom don't see what happens in the room, correct? That's a little regrettable.
Yeah,
right?
They couldn't
Yeah,
get that camera.
at least you can see the speaker, but there is no feedback from the room. But we have about, you know, some 20 people already who are here, and I'm sure more coming. And
Um, and then we will get started with Louis's talk.
Well, I guess if there's questions along the way, somebody there can let us know and interrupt us.
But by the way, can anybody from the room speak just to test? There should be microphones. Can anybody speak from Kishan? Can you hear?
Not really.
No, it's
No.
not. It's not coming. So right. We'll either relay the question. Well, I think this is the time to get started anyway. Okay, so my name is Max Bonament, and really glad to have you here for this workshop on statistics and astronomy. Okay, it's a particular pleasure for me to have a good combination of both areas and more, to tell you the truth, including some statisticians proper. So welcome everybody to sys2025, and really what I would like to do here is only to start this workshop by reading a quote from, can you see this book? This is Louis's book that he wrote, Professor Lyon's book that he wrote 1986. If I recall correctly, I was in high school, and let's say that year, Italy was the defending World Cup champion, but we didn't defend it, okay? But we were happy to have it won 4 years later. And so it says, the result of this experiment was inconclusive, so we had to use statistics. I don't know, raise your hand if you don't relate to that, okay? I personally can relate to this, and this is actually one of the reasons why we are here. And with that, really, I would like to simply leave to the introductory talk to Professor Lyons, and so who will set the scene for this workshop. Louis, the floor is yours.
Okay, so thanks very much, Max. Thanks for organizing the meeting, and I'm sorry I can't be with you. So this is just a sort of really an introduction to the subject of systematics, and it borrows heavily from a meeting that we had, a FISTAT meeting in 2021 on the topic of systematics, and this is the link to the website. FISTAT, for those of you who don't know, it's a series of meetings of various types that we have since the year 2000, and it's on the statistical issues that arise primarily in particle physics analyses, but also in related fields. So I found this quote that is quite useful for this meeting, quite relevant. It's from the Bible, from the book of Psalms, Psalm 19, verse 13, plus or minus 1. And my translation of this is, "Who can understand errors? Save me from hidden effects." Hidden effects, of course, being systematics. So let me just get rid of it. Okay, so let's start with real basics. What are systematics? So we are assuming that we're performing some statistical procedure. We're either measuring a parameter, or we're setting a limit, or we're rejecting hypotheses, or whatever else. And there are two sorts of uncertainties we have to worry about: statistical and systematics. So what are statistical uncertainties? They arise from the limited accuracy of measurements, either due to the machine or to the human being who's connected to it. Or they are Poisson fluctuations in counting experiments. The uncertainties due to statistics usually reduce as we get more and more data. If n are the number of data points, usually the statistical uncertainties, they'll go down by 1 over the square root of n. And analyses with different data sets are uncorrelated. And one way, not necessarily the best way, one way of determining statistical uncertainties is just by repeating the measurements and seeing what the spread of the measurements are. Now we come to systematics. There are for example, the uncertainty in calibrations that we perform, but there are many other sources of systematics too. They're not measurable from the spread of results. The effect of systematics can be to shift the measurement from the true value, producing a bias, but it doesn't necessarily spread out the results, so we can't use the spread of the results to estimate it. With more data, we don't automatically reduce the magnitude of the systematics. We'll talk more about that on the next slide. Between different analyses, the systematics can be correlated rather than the independence of the statistical uncertainties from different data sets. It sometimes can be ambiguous whether you call an uncertainty statistical or systematic, but that's not very serious. And it's more difficult to estimate the systematic uncertainty than the statistical uncertainty, and more open to personal judgment. So it's really important to understand systematics. It's sort of universal in analyses. Almost every analysis has its systematic uncertainty. And it should be, if it's not taking you more time to estimate the systematic uncertainty than the statistical uncertainty, you're doing something wrong. Statisticians usually describe these as nuisance parameters, the systematic effects. If you want more to read about systematics, then go to the PhiStat Systematics website, and it's down here. And we'll illustrate what I've just been talking about on this slide more by the example, a very simple example of a pendulum experiment. Okay, so here's my pendulum swinging, and we're using it to, it's sort of, maybe it's even the first experiment you do in practical laboratory physics. Okay, so we time the swing of a pendulum, and we use it to estimate little g, the local acceleration due to gravity. That's our parameter of interest. And what we do is we measure the length of the pendulum and the period of the pendulum. And we have this formula, tau equals 2 pi root L over g. So tau and L are the measured variables, and g is what we deduce from this formula. So the statistical uncertainties are just due to the accuracy with which we can estimate the period of the pendulum and the extent to which we can measure its length. And that's very straightforward. Systematic uncertainties, okay, there are systematic uncertainties on the variables that we've measured due to the fact that maybe our ruler isn't correctly calibrated. I mean, it's a metal ruler that expands and contracts with temperature, and it was calibrated at a different temperature. That can cause systematic uncertainties, and similarly, we can have systematic uncertainties in tau. The problem, though, to understand the systematics on L and tau from the calibration, we can perform a subsidiary experiment to estimate them. For instance, for L, we can measure something whose length is known. It might be a standard meter that used to be kept in Paris, and that will tell us how accurately our ruler is calibrated. Now, this statistical, as I mentioned on the previous slide, the statistical uncertainty decreases with more data, but the systematic uncertainty doesn't necessarily decrease. You have to do more work to sort of keep it down. So for instance, if I measured my height with a ruler, I might measure it to an accuracy of 1 millimeter. Statistical uncertainty. Now, if I repeat that 1,000,000 times, which I don't intend actually to do, but if I repeated it 1,000,000 times, the uncertainty, the statistical uncertainty, we would expect to go down perhaps like square root of 10 to the 6th. And so is my height now known to an accuracy of 1 micron? And the answer is no, it's not going to be that accurate because of systematic uncertainties that don't decrease as I increase the number of measurements. We already mentioned the correlations on the previous slide. The problem about these systematics are easily to identify, the uncertainty in calibrations. The trouble is that there are other systematics too that don't immediately sort of hit you in the face, apart from the calibration uncertainties. And that is, for example, the formula, this formula here for tau equals 2 pi root L over G, the derivation of the formula requires several conditions which might or might not be true in the actual experiment we're doing. For instance, it requires the angle of swing of the pendulum to be small, so that theta and sine theta are approximately the same. That's not necessarily true for the actual swings of the pendulum that we're timing. So we get a systematic error from that. What do we do about it? Well, either we improve our formula, actually taking into account the difference between sine theta and theta, or we can sort of do the following. We can sort of measure the value of little g from this formula using a given angle of swing, and then sort of start it with a smaller angle of swing and so on. And then we can extrapolate those measurements to theta equals 0, where this formula is essentially true. There's another systematic, a more sort of, again, a different sort of theoretical systematic. Maybe we want the value of little g at sea level, and our lab where we're doing the experiment is up a mountain. So what we do is we consult geologists who will tell us how much material there is in the mountain and what the mountain is made of and so on. And so we can do a correction for the fact that we are up on top of the mountain, and we can correct our level down to sea level. It's possible that we might consult more than one geologist, and each one has their own correction that they provide us with. And so we now have two different corrections, and they might not quite agree. And so we have a problem to know which one to take, and that is again a source of systematic. Even with one geologist, we ought to include a systematic on the correction. If you want to read more about systematic errors, there is an article. Here's a link to the article in the Annual Review of Nuclear Science on systematic errors. Now, oh, sorry, wait a minute. I don't know why it is. Okay, so there are, as I said, there are different sorts of systematic uncertainties. Pekka Sinervo, in a talk at one of the a FISTAT meeting in 2003, sorry, classified them as the good, the bad, and the ugly. And basically, the good are when you do your own calibration. The bad ones are using other people's results, which you might not quite understand how they did their analysis and the model assumptions and so on. And the ugly are like the different theoretical estimates, or the theoretical correction, the theoretical formula you're using involve a power series of different terms of smaller and smaller corrections, and there are only a limited number of terms, so some of the corrections have been omitted. So those are the ugly ones. Okay. Right. When you quote your result, it's usual to quote the result as the best for mu, the parameter of interest, as the best value of the result, plus or minus the statistical error, plus or minus the systematic error. And maybe you quote the total error as the sort of sum of these two uncertainties in quadrature. Whereas in the main part of the paper, it's a good idea to list all the separate contributions to that make up the total systematic uncertainty. So why do we sort of separate the statistical and systematic uncertainties, and why do we quote all the things separately? Well, the statistical uncertainties are usually more reliable than the systematic ones. So if the systematic, it's better to have an experiment with a certain statistical uncertainty and a smaller systematic uncertainty than the other way around. So that's one reason. The next reason is that correlations between your measurement and another measurement can be important. And if you separate these two, you can see how they contribute. And in principle, your result can have a reduced systematic in the future if one of the sources of systematic is better estimated. I mean, you might rely on a measurement of the lifetime of something, and if the lifetime is better measured, then you can sort of see how much to correct your answer by and how the systematic uncertainty decreases. Okay, frequentist and Bayesian probability. There's this ongoing discussion, especially among statisticians, about whether you should be using frequentist or Bayesian approaches. It turns out that the world of particle physics prefers the frequentist approach, and almost everybody else in the world seems to be Bayesian. And there is actually one session in this meeting on Bayesian methods and simulation. So the basic difference in one sentence or two is that the frequentist probability is based on repeated trials, and it's not suitable for one-off situations or for physical constants, etc. Whereas Bayesian probability is degree of personal belief, and it's okay for one-off situations and physical constants and so on. So here's a picture of Bayes, or I should actually say it's the picture of Bayes, because basically it's the only picture of Bayes that exists. And what's more, historians are very dubious as to whether this really is a picture of Bayes, because his haircut and clothing and so on don't look consistent with somebody who passed away in 1763. So the question is this Bayes? What's the probability that this actually is a picture of Bayes? Now, clearly that's not frequentist probability, because there are no repeated trials possible of this. And so the question of what is the probability of this being Bayes is Bayesian probability. And I think that's sort of quite amusing. Right, okay, so let's continue. Right, this meeting, as Max indicated, has a mixture of people from different disciplines. And in 2012, I organized a meeting at SLAC, and that dealt with topics which were of sort of ongoing measurements and experiments that were ongoing at SLAC. So we had a mixture of high energy physics, astrocosmo people, atomic physics, plus statisticians. And the people from the different disciplines didn't know each other. So you never, if you bumped into somebody in the corridor, you might not know which type of person they were. And so I devised this method of finding out, and that was to ask each one of them, what is the value of H0? So if it was a high energy physics person, H0 is the Higgs boson. Its worth is a Nobel Prize, and in fact, the theoreticians who thought of this did get the Nobel Prize for it. So that's the answer for high energy physics people. Atomic physicists would say H0 is the neutral hydrogen atom, and it's fundamental to the whole field of atomic physics, so it's really basic. Astrocosmic people would say the value of H0 is 70 kilometers per second per megaparsec, and the statisticians will say H0 is the null hypothesis for goodness of fit and for hypothesis testing, and so it's very basic. So problem solved, and you can find out who's who by asking that simple question. Okay, systematics and what you do with them. And Max is giving a talk later in the meeting on models for systematics in count data. So there are various methods of incorporating systematics in your analysis. And what you want to know is if you're aware of some source of systematics, how do you find out how much it affects the answer by? So you can do simple uncertainty propagation, and that's okay if the uncertainties are small. You can do it by sort of a chi-squared fit to your data, taking into account the covariance matrix, which includes the systematic correlations. There's the likelihood approaches where you include the nuisance parameter as a constraint based on the subsidiary measurement. The Bayesian methods where you have the posterior, you do the subsidiary experiment, you use your Bayesian technology to estimate the posterior for the nuisance parameter associated with that systematic, and that becomes the prior for the main measurement. You can use a frequentist approach, which involves the Neyman construction. I don't have time to go into that, the Neyman construction now. And that includes a method that's popular in particle physics, a particular version of the Neyman construction called the Feldman-Cousins approach. There are sort of mixed Bayesian and frequentist methods where there is, for the main measurement, you would use a frequentist approach, whereas there's a Bayesian approach for the nuisance parameters. That's the Cousins and Hyland paper. So Bob Cousins will say that on Mondays, Wednesdays, and Fridays, he's sort of very happy about this method of incorporating the nuisance parameters by this mixed method. But on Tuesdays, Thursdays, and Saturdays, he's a bit embarrassed about using Bayesian and frequentist mixtures of analyzing the data in the same thing. And sort of in the last few years, machine learning methods have become more popular. I think there's a talk by Oishik Ghosh about this later in this meeting. If you want to go back to the Biostat systematics meeting, for which there was a link earlier on, there's a talk by Kyle Kramer on, again, different machine learning methods for including nuisance parameters. And carrying on with this theme of including systematics to get the uncertainty on the parameter, there's the method called OPAT, which stands for one parameter at a time. We assume we've got several sources of systematics. What we do is we change each systematic. We go up and down 1 sigma in its value from its best value. So nu is our systematic here. Mu is the parameter of interest. And as we vary our nuisance parameter, the answer changes. And so we just see how much it changes by as we change by plus and minus 1 sigma. And you either can do that sort of like in this discrete way here, or you can use Monte Carlo to generate a series of new values centered on nu naught and with a standard deviation sigma. And again, you get a spread in mu values from that. Another approach, if you've got a better approach actually, is to vary all parameters at once rather than just one parameter at a time, and then add up the effects, assuming they're independent. You add them up as again, you do this sort of quadratic sum of the independent effects. All parameters at a time, if you do that, you get the effect of the correlations automatically. Okay, so I was telling you that at least this talk is based on Weistat systematics from about 4 years ago. So just a few words about the Weistat systematics meeting. The emphasis there on the meeting, needless to say, was on systematics. And the emphasis was incorporating systematics into the analyses, what I was just talking about on the previous couple of slides. Of course, what you have to do is to decide how big the systematic effect is. And that's a sort of, if you like, that's a different topic. It's certainly interesting. We did not include that in Weistat systematics in that we thought that this was sort of like individual to each particular analysis of estimating the magnitude of the systematic. Whereas statisticians who are with us for the meeting, and we regard statisticians as an important part of the Weistat meetings, statisticians would probably be able to offer more help on this side of it, of incorporating the systematics in the analysis. Anyway, the summary of sort of like the talks that we had introductions very much like this meeting by David Van Dyke and me. We dealt with specific areas of particle physics and the systematics they had. So there was the physics at the Large Hadron Collider in experiments involving beams of neutrinos, dark matter searches, and what's called flavor physics. We had specific topics within the incorporating systematics in the analysis. So we had things like mismodeling, the machine learning that I've already spoken about, what you do about theory errors, which are the ugly in the good, bad, and ugly classification, how to deal with unfolding. Unfolding in particle physics is the smearing effect of the apparatus. It sort of vaguely corresponds to the point spread function in astrophysics. And we had a talk on the sort of the bootstrap method of analyzing things from the inventor of the bootstrap, Brad Efron. We had quite a few statisticians at the meeting, and we had short talks by statisticians. And the statisticians, by and large, we had responders for some of the talks. By and large, these were statisticians, and we had a couple of concluding talks. For the meeting, we put up before on the website of the meeting, we put up a list of topics for discussion, and this and the next slide are the topics for discussion, and we had a special version of this on. Here's the website for the special version. We had a special version of this, sort of trying to make the comments down here more intelligible to statisticians and probably other scientists who are not particle physicists. So I am not going to go through these one by one. Oops. So you can read them for yourselves and think of, if you come up with great answers for them, send me an email. So that was the list of topics for discussion. And here, just for interest, is something about the statisticians that we had at the meeting. As I said before, we regard them as an essential part of FISTAT meetings and seminars. They were very welcome, either being present at the meeting or remotely. And we really tried to encourage discussion and interaction between physicists and statisticians, particle physicists and statisticians. And we missed out on live interactions, and we were sorry about that because we think they're very useful. But it was the middle of COVID, so we couldn't have a live meeting. So the statisticians we had there were talks by statisticians, the introduction, as I said, by David Van Dyke, Brad Efron talking about the bootstrap, unfolding, and a statistician giving a summary talk. Most of the responders were statisticians, and we had short talks by the statisticians down at the bottom here. And we had this sentence somewhere on the website: hopefully in future, we'll have the chance to have live meetings like the present one in Alabama. So our hope for the future, as of November 2021, was, well, we had the summary talks. We wanted feedback from physicists and especially from statisticians. And there was the possibility of having more meetings, short seminars and so on. And especially the idea of having a meeting like the present one, Systematics 2025. So enjoy the meeting. I'm sorry I won't be with you. I'm not with you in person, but best wishes for the rest of the meeting.
Thank you very much, Louis. Yeah, what a way to kick off this meeting. Okay, here I have a question for you, if I may, Louis. So, what is your personal Bayesian probability of that being really the picture of the Reverend Bayes? Because I didn't know there was a controversy, and I.
Yeah, never having met Bayes myself, it's hard to say. So, and also I'm a particle physicist, so I tend to be frequentist. So a frequentist would say, I'm terribly sorry, that's not a valid question. Either it is Bayes or it isn't. And it's simply our ignorance that prevents us from giving you a reply. But I think sort of hidden in every frequentist, there's a sort of Bayesian inside hiding there, trying to get out. And so my Bayesian probability would probably be below 50%, in that the experts claim it's anachronistic.
Yeah, it does seem like the crew cut. That seems to be a little, yeah. So to me, that tipped me off as well. Well, this is wonderful. I wonder if anybody in the room has any questions for Louis. Yes, yeah.
I think that book about physics is available online.
Yeah, the question is whether there are the proceedings of the FISTAT meeting. Yes, they are. They are there, and so this is actually wonderful. You know, I believe that you're right. Anyway, that was the question. Yes, Louis.
Yeah. Okay. So the answer is you have to go to the FISTAT website. I find that just by typing FISTAT into Google. So if you go to the FISTAT website, then it has all the meetings there that we've had in the past, and by and large, we've got videos of all the talks. So you're not restricted to seeing just the slides, but you can actually hear the talks. So if you have trouble finding it, send me an email.
Yeah, thank you very much. So I would like to, I don't know if you get the applause coming through Zoom, but, thank you, Louis, once again. This is it's wonderful. Thank you.
So thanks for inviting me to come and give a talk.
Our pleasure. And I believe that yep, David will be giving the next talk. He's a professor of statistics. So here we have an opportunity precisely to start off the meeting by hearing from a physicist and then from a statistician. And I wonder, David, if you if you are ready to go, the floor is yours.
I am. I think you're seeing my slides now. I can see them through the little window on the side behind you.
We are all set. Thank you. Yeah.
Excellent. So I'm delighted to, I'd like to say be here, but I'm not there. I'm in London, about 500 meters away from Reverend Bayes' resting place. And I was asked to talk a little bit about some methods for systematic errors in astronomy. So I'm going to talk about two specific sets of methods. Sorry. Two specific sets of methods that I was involved in developing. So to set the stage a little bit, we all know that in astronomy, like everywhere else, really in science, or massive new data streams are coming online all the time that are opening up new opportunities for scientific understanding and discovery. In these kind of massive and high quality data are allowing, in the context of astronomy, us to model physical processes in a very detailed way. In practice, how that often manifests itself is by multiple analyses, different groups of researchers working on different parts of the problem, and maybe one group of researchers using results from another group of researchers in what I call multi-stage analyses. And these different groups of researchers are going to have different expertise, different data resources, different assumptions that they've made, different statistical methods that they've used, and passing results from one group as an output into another group's input of another statistical analysis is a good way to develop some sorts of systematic errors. So we wanted to think about how we can develop statistical methods that are designed to account for those sorts of errors that can fully quantify or well quantify both statistical and systematic errors. So that's kind of the framework I want to think about. I'm going to talk about two examples. At the bottom of the slide, you can see there's StratLearn, which is for a very specific kind of problem, which is common in astronomy, where basically you're trying to learn about a population of sources and you have a sample, but that sample is not fully representative. So anyone who's worked with astronomical data knows that higher redshift, dimmer, and more distant sources are less likely to be collected in a representative way in a data set. So how can we account for that? So if the data itself is not representative of the population, our estimates of the population are likely to be biased, which is a kind of systematic error. And then after that, I'll talk about pragmatic and fully Bayesian methods, which are specifically designed for these kind of multi-stage analyses. So starting with StratLearn, this is, again, thinking about ways to deal with non-representative data. Can I learn about a population from a sample that only partially represents that population? Okay, so let's think about how we might set this up. And often this is going to be, we think about things from the point of view of supervised learning, where I want to learn a relationship, a prediction or a regression. I want to be able to predict the value of y from x. So x is the number of observations that I have. Maybe, for an example, I'm trying to predict the redshift of sources from their photometric magnitudes. So y is the redshift and x is the photometric magnitude. And the way that I'm going to do that is I'm going to use a training set where I observe both. And to observe the redshift, I probably am going to be using spectral data to learn the relationship between the variables. And typically, I say that, for example, by minimizing the expected loss in a machine learning context. And then I'm going to apply that prediction function to another data set where I don't observe the redshift, or I only observe the predictor variables, but I don't observe the variable of interest. And so I'm trying to, extrapolate and do prediction outside of my sample. And that's all reasonable enough, so long as the two data sets or the two populations are sufficiently similar. But in astronomy, as well as lots of other places, that's not always the case, because by virtue of the data that I'm using for the tuning, it's a more high, or training, it's a more high quality data set, like spectroscopic data, that I want to expand to places where I don't have that high quality data, say only photometric data. And because spectroscopic data tends to be more readily available for brighter nearby sources, there might be some bias that I need to worry about, or systematic errors that I need to worry about if I roll a method like this out. So here's just maybe just a reframing of what I just said. This is a kind of histogram of colors and magnitudes of a sample of spectroscopic and photometric data. The dashed line is the spectroscopic data, and in particular in the R band, that magnitude, you can see that brighter sources are more likely to have the spectroscopic data. And the difference between these two distributions is the manner in which the training data is not representative of the test set where I want to deploy the model that I learn. So let's try to formalize this a little bit more statistically. We're going to be looking at a particular form of non-representativeness known as covariate shift. So now I'm writing this down statistically in terms of conditional distributions, where there's the relationship between what I'm trying to predict and what I have between y and x in the training set and the target set. And I'm going to assume that those are the same. So the relationship between photometric magnitudes and redshift is the same for nearby and more distant objects. The problem is not about what the form of the conditional distribution is, but the fact that my training set and test set differ in their distributions of the photometric magnitudes. So that's the setup for covariate shift, is that the conditional distribution, the training distribution, or the predictive distribution I'm interested doesn't change, but the only thing that changes is the distribution of the predictor variables. Another example down below is supernova classification, where I'm looking for a particular type of supernovas, in this case, type 1a supernovas, which are colored orange, and the non-type 1as are colored blue in this picture here. And I can make that distinction again using spectral data. Pardon me. But I'm interested in using that prediction in a larger data set where I have only photometric data, which are the gray dots in the bottom, which are, from the scale, you can see higher redshift and dimmer objects. So again, the same problem occurs. I believe the relationship is the same, but the domain of my data differs between the training and the test setting. And how we're going to approach this is taking a page out of really public health, controlled trials, where we often, statisticians often think about differences between what we, in that case, would be the treatment group and the control group, and how we can correct for that. So let's kind of think about what just a basic designed experiment in that kind of a situation would be. I have a drug, and I want to see how effective it is in the general population. And the way that I'm going to do that is I'm going to divide a group of patients into treatment and control. The control group would maybe get a placebo. The treatment group gets the active drug. And I want to see if there's a difference in how the outcomes are for the folks who got the pharmaceutical product and the folks who got the placebo. But that experiment is going to have a problem if there's a systematic difference between the control group and the treatment group, other than the fact that they got the treatment. So if people from different socioeconomic classes, for example, end up more likely to be in the treatment group because they're more willing to sign the disclaimer that they're willing to take part in a controlled experiment and be in a treatment group, we might see that's related to, economic outcomes, and then their access to health, and so that there's differences between the treatment and the control group other than the pharmaceutical. And so, of course, the gold standard is to randomly assign people to treatment and control, and only assign people who are willing to take the treatment, the experimental drug. Only those folks would be eligible for the experiment. But in many cases, that's not really possible. If you're trying to look at, say, something like the effects of smoking on health outcomes, you can't randomly assign people to be smokers for decades on end. So statisticians have developed methods to deal with what are called observational studies, rather than designed randomized studies, where we're looking at data from the real world and trying to deduce causal relationships. So a common method is what are called propensity scores. And the propensity score is defined here as the probability that an individual is in the treatment group, given a wide array of covariates to describe them: their socioeconomic class, their economics, their race, their health conditions, health backgrounds, gender, all those sorts of things. Who's more likely, or what is the probability that a person with this set of covariates would end up in the treatment group? And then there's a mathematical result that shows that this propensity score is what's called a balancing score. And that means that if I fix the propensity score, the distribution, or if I condition on the propensity score, the distribution of all of the covariates are going to be the same in the control group and the treatment group. So that, you think of X as being a large group of variables that I would like to be as similar as possible between the two groups. If I can control for a single univariate variable that balances all of the other variables. So that's a nice mathematical result, but it's also has a nice practical effect that I can check this quite easily in an experiment, because I know the X variables for everybody. So I can control for the propensity score and just look at histograms of all the other variables, for example, and see if they in fact have the same distributions if I control for the propensity score. So how can we take that to our kind of machine learning setup? So what we're going to do is we're going to use the propensity score. Instead of being the probability that an individual is assigned to the treatment, we're going to use it as the probability that a observation is in the training set. So just like before, we wish to predict Y, which maybe is the redshift, from a set of covariates like the photometric magnitudes, using a prediction function that is estimated on a training set. And in this context, we're going to find the propensity score to be the probability that an individual stellar object, for example, or astronomical object more generally, is in the training set given its covariates. And then we're going to condition, when we do our analysis, on the propensity score. So what does that mean? We're going to notice, because this is a balancing score, the propensity score is a balancing score using the same mathematics as we use in the public health setting, that the conditional distribution in the target, the joint distribution of what I'm trying to predict and my covariates is the same in the training set and the target set if I condition on the propensity score. And what that means is that, how we do this operationally is we use the training set to estimate. So down here, we try to minimize a loss function for our prediction function. And we're going to do that in the training set because that's the only place we can, because it's the only place that we observe Y. We're trying to minimize the least square between our predicting function and Y, for example. And because of the mathematics of the propensity scores, even though we're doing the minimization in the training set, it's exactly the optimal predictor variable also for the target set. So that's quite nice. And so let's look at it, what it actually looks like in practice. So one thing here is that we have to have this propensity score. Where are we going to get it? Well, we can estimate that from the data, because for each individual object, we know for all objects, we know, for example, the photometric magnitudes, and for all objects, we know if we have the spectroscopic or not. So we know whether or not it's in the training set or not. So we can do a kind of a binomial or a binomial outcome regression to a binary outcome regression, I should say, to estimate the propensity score. So you can see in my notation here, I've put a little hat on the propensity score because it's estimated. And then to see if the estimation is working properly, I can look at these two distributions in the same way that we did, as I described in the public health setting. We can just look at the distribution of the predictor variables, so the photometric magnitudes, conditioning on the propensity score, and making sure that they are reasonably balanced. And if they're not, then I go back and try to do a better job estimating the propensity score. And then given the estimated propensity score, we minimize the expected loss and compute the predictor variable separately or conditionally on the propensity score. And the way that we have done that operationally is essentially we just categorize or stratify the data based on the estimated propensity score. So this is a picture of this supernova classification data where I've separated into 5 different classes based on the propensity score. Now, this was a propensity score to make the beautiful strata here, where the propensity score was based only on these 2 random variables. In practice, we use lots of other variables, and so the strata become a little messy in any plot like it is at the bottom, but the method is exactly the same. We first stratify the data, and then we deploy our learning algorithm separately in each of the strata. Okay, so let's look at a couple of examples. So this is Well, this is the classification of supernova. And the reason that we want to classify supernova is because type 1a supernovas can be used to investigate the expansion history of the universe. So Hubble made the observation that distance is proportional to velocity, kind of a linear relationship. And we all know that velocity is relative velocity is proportional to redshift. So you can estimate distance with redshift. Looking more closely at more modern data set, however, if you plot distance, I'm sorry, this is velocity against distance, you can notice, and this is the residual plot at the bottom, but you begin to notice that the relationship isn't quite linear. And there's cosmological models that are measuring that distance, measuring that lack of linearity, and using it to measure cosmological parameters relating to the volume and the density of, for example, dark energy. So if we want to do that, however, now we need to have a new measure of distance other than redshift, because we want to compare essentially redshift with distance to see this lack of linearity. And so the way that we do that is with type 1a supernovas, so the specific class of supernovas that are very special because they are all similarly bright when they kind of explode. So they have a common physical process that leads to their explosion, where you have, for example, a white dwarf star that's happily cooling over time, and then it acquires significant mass because mass is accreted, so that it exceeds kind of its maximum stable mass, and then it explodes. And so what's special about these stars or these explosions is they all have the same common history, where they exploded from a star of a similar mass, and so their intrinsic magnitudes or their absolute magnitudes are very similar. And so we can look at the apparent magnitudes and the absolute magnitudes, and they differ by that's the distance modulus. So they differ by this function of redshift that's somewhat nonlinear in ways that are controlled by these cosmological parameters. The key here from our point of view at the moment, though, is that we absolutely need to do our very best job at identifying the type 1a supernovas, because if we have non-type 1a supernovas in here, it's going to lead to systematic errors, biases in our results, because we're going to have contamination in the data set, kinds of stars, or not stars, supernovas, or transient events that don't have this kind of the same physics. So we're going to end up with a two-stage analysis, one where we classify stars into type 1a or not type 1a, and then we're going to follow it up with a Bayesian hierarchical model to estimate the cosmology. So we're going to, for the moment, focus on stage one, where we're classifying the supernovas. And what is that going to look like? So maybe just taking a step back at what StrataLearn will look like in a problem like this. So we have data sets in different photometric bands over time, light curves, of the exploding supernova. And we want to use these to classify into type 1a or not type 1a. So to make a commonly interpretable data set, first we're going to fit a Gaussian process to the light curve so we can evaluate the explosion on a fine grid, equally spaced over time, that's common to all of the data sources. And then we're going to reduce that to a set of covariates that's going to fit into our machine learning algorithm using a diffusion map, which you can think of as like a principal component analysis, but allowing for nonlinear relationships. That's going to give us a set of predictor variables. That was the X in my notation, 102 in this case, a large number of covariates that we then use to predict via a random forest which are the type 1a and the non-type 1a, using spectroscopically observed data sets, because those are for the training, because those are the ones that we can determine if they're supernovas or not directly. And the result is measured here. This is the ROC curve. So essentially, the ROC curve is going to tell us how good of a job our ultimate classifier is at separating, in this case, type 1a supernovas from non-type 1a supernovas, where we plot the false positive rate on the x-axis and the true positive rate on the y-axis. And so a perfect classifier would essentially go straight up to 1 and then across. And a random classifier that was just randomly deciding which one was type 1a and not type 1a would follow the 45-degree line. So the further up we can get our curve, the better our classification is. And so here I'm comparing a number of methods. StratLearn is the blue one at the very top, so that's good. The other ones are various weighting methods, which are other methods to deal with covariate shift, where you want to minimize the target loss, and what they do is they use a weighting function inside of in the expected for the training set, which corrects for the difference in distributions between the target and the training set. The problem with these methods is that the denominator here, we're going to be looking in places where there's not very many places in the parameter space or the data space where there's not very many sources in the training set. And so that means this denominator tends to be a number that can get quite close to 0, and these weights can become highly variable and unstable. And so mathematically, this thing is actually, the weights gives you exactly the right thing. The problem is in practice, estimating these weights can be very unstable. So you find that the classification ends up not being as good. Okay. So another example is PhotoZ, which is finding the conditional density of the redshift as a function of the, so right here, it's going to use the conditional distribution of redshift given a set of photometric magnitudes. Same problem as we talked about before, where the source and the target or the spectro and the spectroscopic and the photometric magnitudes have different distributions. And so we want to correct for that. I won't go into the details of the data. And I kind of want to look at this relatively quickly too. So this is kind of a kind of an ugly function at the top, but we need a loss function or a risk function, which is the expected loss of this f function. The f is going to be, again, the condition, our estimated or our fitted conditional distribution of the redshift as a function of a number of covariates. Let's leave this aside. This is, I could try to explain why it has this functional form, but it's a way to fit a whole function all at once. And then we have to, so this is, we want to find the f that minimizes this loss function, and there's a number of different methods. The estimates are a bit more complicated because we want to have kind of a non-parametric estimate of this density function. So there's these various kind of NN is nearest neighbors and kernel-based nearest neighbors and histogram-based nearest neighbors. Series is a basis expansion. So there's different methods that people use. What our innovation here, though, is to do this, to introduce these propensity scores to adjust for the non-representativeness of the photometric data vis-a-vis the spectroscopic data. I should say that the other way around. The non-representativeness of the spectroscopic data versus the photometric data where we want to deploy our method. So just maybe skipping to the results. The x-axis, the y-axis here is the target risk. So that's a measure of how far away from the actual redshift our estimates are. So we would like these to be as low as possible. The blue on the right is our StratLearn method. The black one on the far left is if you just ignore the problem altogether and just proceed with your method without any correction. And the other colors in the middle are various weighting methods that suffer from the problems I was describing a moment ago. And then the 4 columns correspond to 4 different non-parametric estimates of the conditional distribution. This COMB for combination on the right is generally the one you would expect to be the best. But again, we want to try to do better than the best in terms of correcting for the non-representativeness. And you can see here that the strat-learn tends to be among the best, and particularly in this combined method here. As you go from right to left in these three panels, essentially what we're doing is we're trying to fool the methods a little bit by increasing the size of the parameter space or the data space. So there's 5 photometric magnitudes. So this is kind of the closest to the real science problem. But generally speaking, when we try to correct for these sorts of biases, we want to include as many relevant, possibly relevant variables as possible. Because the more variables we include in the model, the more the more dimensions that we can correct for any biases that might exist. So in practice, the general advice for propensity score methods is to include as many covariates as possible, including those that might not be relevant, just in case, because there's no harm. Well, it turns out for these sorts of weighting methods, there is harm. If you include kind of white noise variables, these methods start to do very poorly. But except for this series estimator here, strat-learn continues to do quite well. So specifically in large dimensional problems, strat-learn tends to do quite well. Okay, so let me go on to my next topic. Oops, I'm going to skip that. That's one more example. Another common setting where systematics arise is what I was talking about at the very beginning, where I have these multi-stage analyses. And this echoes some of the stuff that Lewis was talking about, where you have one group of researchers who are, for example, calibration scientists who are calibrating your detectors and passing on calibration products to you for your analyses. And you take the calibration products as given, and they're just values that you use in your analyses, whereas actually they were also estimated using a statistical procedure that could have errors in itself that can lead to systematic errors. So I kind of talked about this at the very beginning, but again, maybe it's worth mentioning. So that the general framework here is we're imagining that there's different groups of researchers who have different scientific data sets, and they have different models, and they make different assumptions. They're using different statistical methods, but they pass on their estimates of particular nuisance parameters, calibration products, classifications of sources, like we were talking about in the previous example, are passed on to subsequent researchers who take them as inputs to their analyses. And by the nature of essentially what happens is the statistical errors in the previous or the preliminary analysis, the upstream analyses, if statistical errors are carried forward, and because you're collecting and using a different kind of data in the subsequent analysis, you're not using calibration data anymore, you're looking at a star and using the calibration to estimate the spectra of that star, the error is no longer diminished as your data set grows. So what was a statistical error in the preliminary analysis becomes a systematic error in the primary analysis or in your analysis. So looking at calibration in particular, this is a little kind of cartoon of maybe an X-ray spectral analysis, where the astronomer is interested in what's going on over here. They have physics-based scientific models for the spectrum or the image in their source. They might be using parametric models with parameters for power laws and things where the parameters have a physical meaning to them. But unfortunately, the data is more complicated, and it has to go through this filter that is the telescope, which involves background contamination, point spread functions, absorptions, varying sensitivity, effective area curves, and everything else before you get to the observed data. And if there's, again, like statistical fluctuations in the calibration of the effective area that are carried on, that leads to systematic errors. So we're going to look in particular at the effects of the effective area curve here. So the way that we're going to do the analysis is we start with this is going to be a Bayesian analysis. So we have a likelihood function using a Poisson model for high energy or X-ray counts, and I have a little power law model here. It depends on, this is the effective area which the astronomer typically is going to assume is known. And because I'm going to do a Bayesian analysis, there's going to be a prior distribution on the theta. That's not going to be what's particularly important. You can use a diffuse prior, and you'd have very similar issues if you did things from a likelihood point of view. Bayes' theorem allows you to combine the likelihood and the prior distribution to get the posterior distribution of the parameters of interest. And from a Bayesian, this is going to be the basis of inference. The problem or the challenge here is that everything is conditional on A. All the way through this analysis, we assume that A is known. A is the effective area, sorry. The effective area curve we assume is known. Y is the data, theta is the parameters. How can we account for uncertainty in A in a more principled manner? So what are the calibration? We worked on this some years ago, and we talked to the calibration scientist, and they provided us with a sample of a Monte Carlo sample of possible effective area curves. And these are some just plots of them, just kind of showing the variability, where the black line in the middle is the effective area that's taken forward and typically used. This is kind of a residual value residual plot that shows you that it kind of blows up the differences there. But what we want to do is we want to introduce a prior distribution that represents this level of uncertainty for the effective area curves and introduce it into our overall statistical analysis. Now, people who don't like Bayesian analysis typically will complain about prior distributions being subjective and not based on the data. But what's important here is that by introducing a prior distribution, we're actually being more conservative. We're not, if the typical thing is to pretend something that has uncertainty, has no uncertainty, you take the effective area curve as given, that's a very strong prior distribution. So if I instead use a prior distribution that has variance, I'm reducing my kind of level of assumptions here. And so what we're going to do is use that same posterior distribution. It's here, this term here was the posterior distribution that we'd had before, but we're going to average that thing over a prior distribution for the effective area. So the calibration scientists provide a sample, a Monte Carlo sample of possible effective area curves that represent their uncertainty. And we have to turn that into kind of a functional form. And we do that using PCA and kind of a low-dimensional Gaussian approximation. I don't really want to go into the details of that, but trust me that that's something we can do. But suppose now we have done that, we have a reasonable prior distribution for the effective area based on the calibration scientist's results. And now I want to think about two different ways that I can do my analysis. And so let's look at the fully Bayesian analysis first. So what I have here, this is just a factorization of the joint posterior distribution of the effective area and the parameter. Okay, this is what a Bayesian would typically do. And you can see that what's key, okay, so, and then I'm going to call that a fully Bayesian analysis. And then above that, I have what's called a pragmatic Bayesian analysis. And the distinction between these two things is whether or not I let my current data set inform my calibration. So what does that mean? So I have calibration scientists, and they have their uncertainty for the calibration product, the effective area that we would like to use. Now I'm doing my individual spectral analysis of my data set. So the question is if my analysis now should impact the uncertainty of the effective area curve, or if I should just let the calibration scientists determine that. So the pragmatic one says the calibration scientist should have the opportunity to represent uncertainty, but my analysis should not really inform the effective area. So maybe I'll just leave it at that. This goes through a bunch of kind of pros and cons for these basic methods. The most important thing is essentially the fully Bayesian method, by virtue of its name really, is the principled statistical way to go. The pragmatic one makes a bit of a compromise because we might think that the calibration scientists probably know have better information for determining calibration products than I do. So let's look at kind of what the results are. This is a kind of a simplified spectral analysis. And what I have here, the purple dot, here's it's a power law. So there's theta1 is the normalization, theta2 is the power law parameter. The purple dot is the true value. This is a simulation study, so I know the true value, the effective area. I have a big data set, so the statistical uncertainty is quite small, but you can see there's this systematic offset because the calibration is off. So my posterior distribution, or it could be my likelihood function, is relatively narrow, but it's off from the truth. That's the default analysis where you just use this effective area, a single effective area curve, treat it as known, even though it turns out it's a bit off. This is looking at the systematic errors. So for each of a large number of possible effective area curves, I fit the spectra. And you can see that these are effective area curves according to the prior distribution. So according to the level of uncertainty that the calibration scientists have for the calibration product, for the effective area. So you can see that the systematic errors, how much my answer moves around depending on the uncertainty in the effective area curve, in this case dominate the statistical errors because I have such good, I have such good data that it's the good data is shrinking down the statistical errors, but it's not shrinking down the systematic errors. The slide on the panel on the right there is then showing you the statistical errors, not, ran across the distribution of the systematic errors. So in this case, the statistical errors all look like they're about the same. The size and the orientation of these ellipses are all about the same. That's not necessarily true in practice, but it turns out to be the case in this problem here. So the statistical, and this is kind of getting back to the kind of thing Lewis was describing, where you would like to report something about the systematic errors and the statistical errors separately. The total uncertainty ultimately is what we're interested in. And this is looking at essentially the same problem, now actually looking at the data analysis, though, rather than these sorts of trying to separate the statistical and systematic errors. What do the posterior distributions actually look like? And so again, the default gives me a nice tight standard error, but it's off from the truth, so it's kind of not very useful. The pragmatic opens that up because it's expanding to account for the uncertainty that the calibration scientists have for the effective area. And the fully Bayesian, now you can see, is narrowing things back down again, because what happens essentially is that each of these points correspond to a particular effective area curve. And some of those effective area curves are less consistent with the actual data that I have. So they get, in the fully Bayesian analysis accounts for that. So if the effective area curves that result in these values of theta1 and theta2 are less consistent with the data, and because they're less consistent with the data, they're downweighted in my final analysis. Okay, so this, I don't have time to go in. I can see that my time is running out. So I don't have time to go into like all of the details of things. But the advantage of the pragmatic Bayes is it's really easy to implement. Generally in practice, you just essentially just rerun your analysis for multiple values of the effective area from a population that represents the calibration scientist's uncertainty. Whereas the fully Bayesian analysis, I actually have to be, carefully fit this more complicated model, which is fine, but it does require a little bit more overhead to implement. So with an interest in not taking time from the next speaker, why don't I stop there and see if anyone has any questions.
Thank you so much, David. Questions from anyone in the room, or yeah, you want to come and speak here? Yes, so that's easier. Yeah.
Thanks for the nice talk, David. I have a question about learning with biased data.
Mhm.
The task of learning the propensity score is presumably still subject to the same numerical challenge as learning the density ratio of train to target. I'm just wondering if you have an intuition why this is easier in practice.
Yeah, yeah. I'm not. What I would say is I'm not sure. I don't want to say if it's easier, but I want to say why I like it better or why it can sometimes perform better. I'm trying to think if I have a good slide to show this. Yeah, well, maybe here. So because we're estimating, we don't actually have to estimate that ratio, right? I'm only estimating the probability. And then I'm categorizing the data based on that probability. So probability is estimating numbers between 0 and 1. Probabilities with things like logistic regression don't become unstable in the same way that estimating a ratio of a density of two densities when one of those densities tends to be close to 0 or very small becomes unstable. So I guess that's essentially the reason. And I mean, there's a kind of a another way to think about it is there's kind of a bias variance trade-off. The weighting method is unbiased. It's that expected value. Maybe if I go, trying to think if I have a good slide for this. Yeah, here. This is an unbiased estimate of the target expected loss. So that's good. The problem is that it's highly variable if you're in cases where there's a part of the predictor space, the covariate space, that's underrepresented in the training set. Whereas what we do, our method is not unbiased, but we trade a little bit of bias to reduce that variance a lot because we're just putting wide swaths. We have 5 strata of this probability. We're treating everything in that has probability greater than, say, 0.8 the same. Everything that's probably less than 0.2 the same. And that kind of histogram introduces some bias, but overall, we think it's worth it because we reduce the variance. Does that make sense?
Yeah, that's a great answer. Thank you.
Yeah.
Right, thanks so much. And maybe very quickly, but so fully based, right? So that's just to clarify because I'm not familiar with that, and I wonder maybe others might have a similar question. So that's the case in which you don't just use a, let's say, constant prior, but did you say you train the prior or something like that, or this?
So I didn't hear the first word. Which Bayes?
Sorry, fully Bayes, right?
Fully Bayes.
Because I'm used to seeing Bayes' theorem, with a prior probability P of A, and that's just P of A. But here it's P of A given Y. So that's like you said, training of the prior with.
Yeah. So this, I mean, I could have, and I wish I could, if I could write, it would be maybe better. This is exactly standard Bayes. When I say fully Bayes, it's just Bayes, and just underlining the Bayes.
Okay.
It's just that because you can see what you're used to seeing with Bayes' theorem, I've already done here. Because this is P of the far right. You can probably see my cursor. This this is the posterior distribution. So if you wanted to rewrite that, it would be P of Y given theta divided by P of Y. Everything is conditional on A. So
I see.
So this is it's just I've just not written it out fully because I've already flipped the order of the conditioning. Because I kind of what I wanted to emphasize instead was this part here. And that is up here, I'm not following Bayes' rule. Bayes' rule says if I have y, and data, y, and I have things that are unknown, theta and a, neither of them are, a is a nuisance parameter, not interested, but because it's unknown fully, y should be treated, y should be treated informatively for everything equally. And I'm not.
I got it. It's just yeah. Thank you. That explains it. So I appreciated that. Wonderful. Okay. So I would say let's thank David once again. This is wonderful. Thank you so much. Yes.
Very good.
Thank you. And yes, John, we are 5 minutes late, so we'll take that into proper account. And yes, and so we go as the Zoom gets ready. Yes, it's my pleasure to introduce John Hakila here, who has not only is a colleague in the physics department, but also an administrator and an expert in gamma rays. So especially pleased to have you here and review some applications of gamma ray bursts.
Thank you. So I'm going to talk about GRBs as sort of an example of systematic uncertainties like dominating everything. And
This is the microphone, by the way. The computer's the microphone.
okay. What I really also hope to show you is something where, as we try to peel down those systematics, we get order from disorder, although it's still not completely disordered, whatever, you know, and nothing's completely organized. So just sort of a quick overview of GRBs. As you probably know, they're high energy, very luminous sources that don't last very long. They're seen in many directions of the sky. They're cosmological in origin. And there are two classes on the basis of durations and spectral hardness. The long ones are associated with collapsars, and the short ones are associated with merging neutron stars. The emission itself is believed to originate in relativistic jets, although for folks that are relatively new to the field, you probably think that we moved on to study afterglows because we had figured out the prompt emission, and the actual truth of the matter is we moved on because we couldn't figure out what the prompt emission was. How do I move it? Let's see, it's the
Down arrow.
down arrow.
How about now? Nothing?
No, I can do it with this. Okay, got it.
Yeah, this down arrow right here.
Okay, got it. Okay, so if we take a look at some gamma ray burst light curves, so these are based on gamma ray emissions, and you'll notice the wide variety of light curves that appear. A former colleague of ours here at the University of Alabama, Huntsville, many years ago, who was also on the BATSI science team, Bill Pachasis, once said, "Show me one gamma ray burst and I'll show you one gamma ray burst." So the idea was that GRBs are all different. And it's very hard then to try to figure out how to, what the physical mechanisms are if you can't find any behaviors that you can associate with them. So in a way, GRBs really are, they are perfect for, as an example of places of studies where systematic uncertainties really dominate the whole situation. We have imperfect modeling and simulations. We have difficulties comparing the results from different experiments. And I'll show you, you know, why in a moment. There's uncertainties in the parameters involved, and in part because many of those parameters are correlated. Spectral evolution is correlated with intensity evolution, and signal to noise is a driver on all of this. It's really hard peeling off what's signal and what's noise. And then, of course, as I mentioned, we don't know what the theory is, so we're not really sure what model we should be applying to the situation. So examples of some of the observational biases that really make the interpretation difficult. Every instrument that goes up has to be an orbital satellite. You can get some balloon stuff also, but it's got to be above the atmosphere. And so the detector surface area is important. The last talk, I think, is interesting because it does sort of focus on problems that you can get at from having different surface areas, even on a measurements of calibration of an individual detector. But here we span decades of observations with multiple instruments that have different detector photon strategies. They have problems with pulse pileup. They have different spectral ranges. So something that one instrument sees as, oh, this is a gamma ray burst, the next instrument only sees part of that. The cadence of the instrument, what's the, you know, the time period of, since these are variable time things, then what's your cadence of your instrument? And of course, when you try to break that information up into different spectral components, you know, you're cutting the number of photons down in each of your energy channels. And so you're, you know, you're turning something that may have been systematic into something that then becomes statistical. And then, of course, we have issues like trigger efficiency and sky exposure. Are you actually monitoring the entire sky all the time for every single burst? No, of course not. Nobody would do that. So you have to have some mechanism for selecting something that's a burst versus something that isn't. So kind of starting off, you know, in the early days, there were lots of analyses using standard light curve analysis techniques, Fourier transforms, power density spectra, wavelets, and so on. And a lot of these techniques found that, gee, we can get some, there are hints that maybe there are quasi-periodic or periodic behaviors, but everything was hidden in the signal to noise problem. And so at some point, you'd say, oh, look, I found this burst that appears to have this quasi-periodic behavior, and then you'd go compare it with another instrument that saw the same burst, and they couldn't see it. So, you know, suddenly you don't really know what the results are. And so the approaches needed to be refined. We needed to come up with some other techniques. One technique that was relatively effective was cross-correlation function in looking at broadband different energy channels. And it appears that the burst energy goes from hard to soft. In other words, it's dominated early by higher energy photons. And as it carries on, whatever happens to the light curve, in the end, it's dominated more by low energy photons relative to the high energy photons. And once we had luminosities, we discovered that some of these really spiky variable curves are, they belong to very luminous sources as opposed to fainter ones. So I think one of the kind of the key changes in looking this was making a definition. And the definition comes from Jay Norris. A lot of it is his pulses are the basic units in bursts, the basic units of GRB emission. But there's a caveat, and it's an important caveat, is that these emission episodes are composite structures. So when we think of a pulse, we think of something that's smooth and uniform. And what he's saying is, or what the results are, is exactly the opposite. Oh, there's this pulse, but it's got hair on it, right? It's doing all this stuff. So, you know, this brings up a root question before you even think about what it is you're trying to physically explain, is are there behaviors that you can find in GRB pulses that identify them as such? How do you model and simulate them? And therefore, you can start asking the question of what causes them. So let's look at some of the pulses. And of course, as soon as people defined these pulses, they said, well, let's pick the easy ones, right? Let's not pick something that's complicated. And so Chip Megan, who is another scientist here at Marshall, who's on the BATSI science team, kind of coined this name FRED, fast rise exponential decay, because it's the simplest light curve that you can see. There's a quick increase and a long decay. What you're looking at over on the right-hand side here are 4 different energy channels seen by the BATSI instrument. The blue represents highest energies up to 1 MeV, and the red represents lower energies down to about 20 keV. Again, that's the BATSI experiment window. Most of the observations I'm going to cite here and most of the analyses I've done during my career work with BATSI because it has one of the largest surface areas of all the instruments, and it has one of the highest signal to noise ratios. Unfortunately, it was up at a time where it couldn't really detect. We didn't have a strategy for detecting counterparts, so we don't really have distances to a lot of these individual bursts. But that's not important for this analysis. What we're really interested in here is looking at the behaviors of the light curves. So you can see some of these behaviors that define what the pulse is doing rather than what the burst is doing. And that brings up the question of, what is the empirical shape of a GRB pulse light curve? So if we're going to try to figure out what's going on, the simplest place to start is by modeling it. And modeling the shape of the light curve, especially if we've identified a simple light curve, is good. Notice there have been a variety of techniques over the years. Every possible model that you can think of something that gets bright quickly and gets faint relatively quickly has been tried. Many of them are pretty good. I mean, they do fairly good jobs of fitting. And so it's not so much an issue of picking one over another. I'm going to pick the Norris function because most of the pulses, as you saw in the last slide are asymmetric. They've got the fast rise and the exponential decay. Starting with that, then it's easy to pick a function that's very good at modeling the fast rise and exponential decay, which is what the Norris function does. So we can look at these FREDs and we can see how they evolve from hard to soft. And as we look at some of the ones with hair, we see that they don't really do, they're not really quite as smooth, and it's not so obvious how they're spectrally evolving. So again, these are 4 different energy channels, and then that's with the kind of the color coding version over here. So it turns out that when you break the pulse apart, the emission into different energy channels, you can fit the energy channels as well, and then you can get some observables out of that. So you can measure things, you know, alternate ways of getting a spectral lag, of getting a duration, and of measuring energy-dependent properties. So that's led to some more involved models. One of the models was by Tom Laredo, who's going to be talking later at this conference, and Bob Nemiroff, who decided to try to mix the spectral evolution with the intensity evolution. So that's kind of a more involved recognition that these two things are coupled somehow. But they don't address what the real problem is, which is the hair, right? Which is the structure. And that's where things, to me, really get interesting, is because if you treat every statistical every fluctuation that cannot be explained by statistics as a statistical variation as a separate pulse, then some of these things that are really complex, you can fit with 50, 100, 1,000 individual pulses, and you have no idea what the shape of each of them look like because they all overlap. So this is an example of the same pulse fitted in 2 different ways. One is by Jay Norris, who had, and this is the 4 energy channel model, where he fitted it with 3 separate pulses that all overlap. And that treats each one then as a separate pulse. And therefore you're looking at the behaviors of stuff that comes from one emission episode as if they are all separate. And over here, we take the assumption of, okay, this is one emission episode. We're going to fit the emission episode using the model. And it's a horrible fit, right? It's a terrible fit. But it does it encapsulates this idea that the whole thing represents a single pulse. So that led to this question of, okay, if there's this leftover stuff, what's the leftover stuff look like? So a number of years ago, we took 54 Batsy pulses. We normalized them all to a same intensity and duration. And then we subtracted out the model fit, took the residuals, and then just added them up with the idea of if those leftovers, that structure is kind of spread evenly, then it should all cancel. And it didn't do that at all. In fact, it came up with this funky looking shape here, which says that the the actual shape of a gamma ray burst pulse has some structure to it. It's built into the structure, even into these simple FREDs. And the model is fit by this, it could be fit with this function over here. And I want to show, and not because I think the function means anything, right? This is all empirical. But the interesting thing is that the function is, it's a real simple function that's the same measured from this vertical point here going forward or going backward in time. It's a sort of a time symmetric thing that's been stretched out. So applying this, if we look at the central panels here, there's a blue dotted line, a dashed line, which represents the Norris fit. And then the residuals are over here. And then there's the residual fit using the model. And then the total thing is mixed together to come up with a really good fit. But over on the right-hand side, what you're looking at is a hardness ratio. So it shows, it's a measure of kind of what the spectrum is doing as a function of time. And so notice that we see this hard to soft evolution of the pulse. But notice the down arrows represent the peaks in this residual function. And every time the pulse rebrightens, it rehardens. So there's a tie between the spectral evolution of the pulse and the intensity evolution of the pulse. And when we add together a bunch of pulses seen by different instruments, seen for long and short pulses, seen in X-ray flares. These are X-ray flares that occur during the afterglow phase. So they're like late pulses in a gamma ray burst. They all follow these same sorts of behaviors. Okay, so let's go try it with some really bright pulses. And it fails miserably, right? Because they have too much structure. There's way too much structure. If you treat this emission episode as a single pulse, the model doesn't work very well. But it does sort of show, when you look at the hardness ratios, that every time the pulse rebrightens, it rehardens. So it's got the same general behavior that we saw for the simple model, but it happens in the complex pulses as well. Okay, so now we've got a question then, which is, what is the effect of signal to noise on our measurements here? How much of this is statistical versus some sort of actual thing that's going on in the burst? And so what's happened here is I've taken a number of those really bright pulses and have reduced their intensity and then added in Poisson background noise again and reconstituted them and then remeasured them. And what you're seeing over here is a measure, an arbitrary measure of complexity, of structure. And by the time you get down to simple here, that's something that now just looks like a Fred. You've washed out everything. And so when the pulses are really bright at high signal to noise, they've got all this structure. And when you reduce them in intensity, the structure goes away. But now the interesting thing is that if we try to measure all of the properties of the pulse at each intensity, so we do it Monte Carlo many times to try to get measurements, this here represents the duration. This represents the asymmetry of the pulse. These are a number of measurements of lag. If these have been done incorrectly, you can blame Dr. Lestrade here because he was the one that made those measurements. But as we reduce the intensity, the uncertainty becomes larger in the measurements, but there's no systematic difference in what happens, in what measurements you make at bright intensity and faint intensity. And that brings us to the inescapable conclusion, unfortunately, that if you want to understand what the pulse is and what's going on, you have to understand the structure. And that means you can't look at the faint ones to see the structure. You've got to look at the bright pulses. So we've gone back, and again, these are the residuals for a number of different these really bright pulses. And what I've done here is I've seen that the structure still has this apparent time reverse thing on it, but the bright ones they don't just end with one bump on each side. They have multiple bumps, but it's the same going forward and backward in time. Whoa, that doesn't make any sense at all. Sometimes the fits aren't super good, but most of the time for the bright ones, they are good. And you can see these here, and it even picks up things that before, in this case, you might have thought this is a separate pulse, but there's another thing on the other side that's also lined up. And when you fold it over so that you get these things to match, those bumps match too. So there's evidence of some sort of time reversibility built into the structure. So let's simplify the residual model. Let's just take the residual model and turn it into a 2-parameter model where we have some time at which you can fold the thing over, and then you have some amount of stretching that occurs, and then try to see what the alignment is to see if we can get a good match. So you've got this 2-parameter model. And here are pulses that have been fit. This is the asymmetry of the underlying fitted pulse using the Norris model. And this is an asymmetry of this residual, the amount of stretching of the residual structure. And like most physicists, I did something stupid when I first defined it. I should have defined it so that they both went together, but I defined this as the inverse, so it actually goes that way.
Keep going.
But this line then represents a true correlation. And then this is using the folding technique. And this is before I had come up with a way of measuring the uncertainties on it, but it shows the same general effect. Okay, well, we hadn't really included really symmetric pulses because the Norris model had trouble fitting those. What if we had a Gaussian in, use a Gaussian when the model is really symmetric? And now stuff gets really weird. If up until now you thought that I'm a crazy guy standing up here just waving my arms, let me show you what happens when we apply this to emission episodes that no one would ever have thought was a single pulse. So what you're looking at here is the black represents the data. The red represents the model built by folding the residuals over. So fitting a pulse and folding the residuals over. You can see the blue line, which represents the 4-parameter pulse fit, and then the 2-parameter residuals. The data on the left side of the line is taken from the data on the right side of the line, folded over and stretched. And the data on the right side of the line is the data from the left side, folded over and stretched. And so here are things that you never would have thought represent a single pulse, which suddenly all these kind of clusters of things sort of match up. It's not a perfect match, right? So making the statistical argument, this becomes, it's a thing that I went back and forth with referees many times on multiple different papers, but eventually the papers got accepted with requests to try the statistics this way or that way or this way or that way. It's not a perfect fit, and in part because of these systematics, but it's still, it's still amazing that all of these things can be fit. In fact, where was it? 86% of BATSI GRBs going sequentially through the catalog. I had not a lot of other things to do during COVID, so I went through the catalog sequentially and started fitting all these pulses. And 86% of them can be fitted using this model. So this is getting the uncertainties, generating them through Monte Carlo techniques. This is the asymmetry versus the mirror function. You can see all of the, the stretching function, and you can see all of the symmetric pulses that have been added in by using a Gaussian fit. And these are the ones with the smallest uncertainties. Very, very strong correlation between these two parameters. This says that the structure is related to the underlying pulse if you treat it as a time reversed function. The two things are related. And there's evidence that we've got two different groups of pulses. We've got symmetric and asymmetric pulses. But a referee asked, why is there so much scatter in this diagram? And so I went back and looked at it. And interestingly enough, I found that when you look at the light curves, that light curves of similar types are, you can sort of color code them in and identify them. So for example, the blue squares here are Freds. And so Freds are asymmetric pulses with asymmetric residuals overlaying. These green dots look like Freds, but they have more structure to them. And they tend to be, the structure tends to be more symmetric. And so we just name them roller coaster pulses. These ones, another one of my students just really liked these, the ones that are very symmetric and they have lots of structure. And he said, wow, they look like crowns. And so this is kind of stuck, this idea that these are crown pulses. But there are some crown pulses where there's not much of an underlying pulse. Mostly what you're seeing is just the residual structure. And these things we call U pulses because they kind of have that U shape. And there are these other ones that at first I thought, oh, they don't have anything to do with anything. Actually, they all look kind of similar also. They all have asymmetric light curves, but they have lots and lots of structure. They're asymmetric U pulses. So these are classes that we just sort of created. They're like 5 or 6 of them. If you use unsupervised classifier and ask them what it thinks, it comes back and says, well, maybe there aren't quite so many. Maybe there are only like 4 classes. But the interesting thing is, see these black dots here? These black dots represent the points that we could not classify by eye using this technique. So this works on the vast majority of the pulses that are on this diagram. There are some that show up that you didn't expect to see on here. These ones look like U pulses. We didn't even recognize them at first because it looks like the episodes are separated by such large times that they must not have anything to do with each other. But I found these, and then Stephen independently found these and called me about them later. So we call these, well, we're not very creative, so no pulse U pulses. The pulses that we didn't fit and don't fit into this categorization are ones that have light curves that we didn't allow for, right? So something that's a slow rise and a rapid decay, because the Norris function doesn't fit that and our Gaussian doesn't fit that. But we do find that there are a number of them, and so these things are sort of crescendo pulses because they reach a crescendo before they die out. And then there are these really long things with complex structures, and we can't fit them with any pulse model because these things don't the episodes don't really work as pulses quite so easily. The interesting thing is that there's an actual class of gamma ray bursts known as ultra long gamma ray bursts, and these sort of tie in perhaps to that categorization. So how robust is the time reversed explanation? Liu and Zhou have gone back and have used a different technique where they assumed that the residual stuff has to be an emission. It can't be an absorption because we don't know a mechanism physically in gamma ray bursts for creating that absorption thing. So they take their Norris function and they reduce it so that all the residuals are positive. And then they try to fit the residuals with the time reverse function. And they also try to fit it with a repeating function where they have the same thing that happens twice in order. And they find that even if they try to force it to fit with this time repeating thing, half the pulses are still better fit by a time reverse model, even when they go around the approach that way. So it looks like this time reverse thing is a real structural component of many gamma ray burst pulses. And another technique that's been used, I just want to throw out there, which is dynamic time warping, is when you think you've got repeated structures that kind of line up but don't exactly line up. Dynamic time warping is a technique that allows you to sort of shift the times and match something from a time that isn't exactly at the same time as the thing you're comparing it to, but try to line it up. And so there's evidence that there is some sort of repeatability in many gamma ray burst pulses. So this becomes the root of the problem then. If we want to learn about gamma ray burst physics, really the important thing is understanding how what's causing the spectrum to change, what's causing it to rebrighten and reharden, what happens between pulses. Does a pulse wait a long time for energy to build up before it re-releases it? And the central problem with all of these is defining what a pulse is. This is a systematic, not a statistical problem. If you define a pulse in a way that every statistical fluctuation is an individual pulse, you have no residual structure, and you have to explain everything by the pulses. If you have a definition where you've got an all-encompassing pulse and everything that's around for the emission episode and everything that's left is residual structure, then you have to come up with a coherent explanation of what that residual structure is. And unfortunately, when you go to the literature, you see many papers where people do not define what they think a pulse is in their analysis, which to me makes it meaningless because now you can't compare it to anybody else's results at all. And you can't even tell whether your results are coherent within your own study. So in summary, pulses are the basic units of GRB emission, but they are dominated. It depends how we treat systematic uncertainties to get anything out of this. And as a postscript, I know that I'm focused on this part of this, but if you're like me, you're wondering what the hell can cause time reverse structure. That's a whole separate thing. We've published a number of papers on this. They're all really weird because this is not a phenomenon that we see that's standard in astrophysics. So anyhow, thank you. And I'm sorry to take up so much of your time.
Questions? Yes.
Thanks for a great talk, John. Can I ask you to speculate about what is causing this first behavior?
So we've had a number of different approaches that we've used. I was going to include slides, but I knew it was already too long. The one that so the standard model is that this jet is pointing at you, everything's coming out relativistically, and the jet, that would mean that anything that you see is happening internal to the jet. So you talk about, internal shocks or electromagnetic effects, whatever you're talking about, It happens internal to the jet. And that's problematic for a time reverse thing because you can have something coming towards you and you can make a bump going up and maybe a reverse shock going back, but you can't make a forward and reverse shock that don't happen independently of each other. So in other words, to have them nested in each other is really, really problematic. So we've come up with a number of different models. One of them involves faster than light emission in the material that it's moving through. So in other words, you've got Cherenkov radiation that's running away from part of what happened before. But recently we had a model that I tend to like better because it's simpler, but it still violates one of the standard hypotheses of GRBs. That is that you've got some sort of a symmetric jet that sweeps across the observer's line of sight. Because now any structure that's built into the jet, the observer will see the first part of it, the center part of it, and then the back part of it repeated. And so this side should look very similar to this side. So that's the simplest model. But thank you, Sukanya.
Can see why, the referee might ask you questions.
Yeah.
This is, wow, what an interesting problem. Yes, Vinay.
So I am completely not an expert in this, so I was wondering, has anyone tried to do an auto-recursive model of light curves that will take away, that might make it easier to find the pulses?
So state that again. So to take away. So not that I'm aware of, I guess in part because we can't even get people to agree on what the model of the underlying pulse looks like. So, it's going to be all of this stuff is going to be driven by the systematics. Another systematic is, if you look at observations by Swift, which is, one of the big satellites that's out there now, it's got a surface area that's equivalent to BATSI. It's a large surface area, but it's only sensitive at low energies. And so, first of all, it misses a whole bunch of the structure because most of the structure is very obvious at high energies. And secondly, the signal to noise at lower energies is much worse. So you lose the structure, even though you've got higher signal to noise. And the Fermi GBM instrument, which is up now, which is basically a little BATSI, it's knocked down a whole bunch of the systematics. And so you can get really good observations, but the problem is that it doesn't have as big a surface area. So it doesn't see a lot of the same pulses and bursts that BATSI saw.
There were slide where there were 6 different models for the pulse, like Gaussian exponential. Are these just empirical or are there theoretical models that can recreate each of these?
No, they are empirical. They are, in fact, it was a response to the referee's question of why do you think there's so much scatter? And I just thought, well, let me look at the light curves and see if I get any insights. And it was amazing how it just kind of popped out that, yeah, there are these things. So again, machine learning techniques didn't find as many of these classes as I had assigned. It doesn't find a whole lot of difference between the U pulses and the crowns, but it still could see the differences between the different pulse classes.
And of course, any more questions, we can ask them over a coffee break, I suppose. So thank you once again.
Thank you.
Right, so we'll, I think that whatever the program says, and we come back at, 10:45. And then there should be coffee right outside.
I do. Okay, that's all right. And then as I started providing the context started becoming more and more, and so I decided to talk instead, slightly a little bit more a more general and more expansive talk. So this is going to take an hour and a half, Max. I'm sorry.
This is
So that's fine, we still go for lunch.
Yeah.
Because-
Yes. So I'm going to talking about the systematic effects that affect analysis of stellar coronal spectra. And I just want to point out that can we see cursors? No, we cannot.
What's next to the laptop?
This one?
The green button is a laser pointer.
Ah. Oh, okay, that works. Very good. So yes, I almost did not make it here because of the shutdown. I'm very really glad to be here. One other thing that I want to point out that everything that I'm going to talk about is done in collaboration with several of my CHASC and ISSI collaboration colleagues. So for example, David Van Dyke will find many of these things very familiar. Okay. All right, stellar corona. So the basic outline is I just, I want to tell you a little bit about coronal spectra, and in particular focus on something called emission measures. This is not a common thing. Now, most astronomers even don't use it. So I'll spend some time to get through that. And then I'll spend the rest of the time talking about where systematics play a role. Okay. So just a very basic introduction to stellar X-rays. This is the HR diagram. Everyone probably knows what they are. There's essentially color and also defines surface temperature of stars versus luminosity, inverted luminosity. And there is a track which tells you where the main sequence is. And the point here is that you see X-rays all over this track, especially in O and B stars early on, where you get X-ray emission from shocks in vents. And in late type stars, starting from F, G, and K, the sun is somewhere here. F, G, and K all the way through M stars. I put two different bubbles over here just to signify that there is a change in the characteristic of how the X-rays are thought to be produced. But in terms of what we actually see, there won't be much of a difference. So anyway, so what do the spectra actually look like? This is a model, this is not a real observation. But what this is showing wavelength across here and temperature going across here. And the several instances of isothermal temperature spectra generated at single temperatures shown along here. So a couple of things you should notice here is that there are streaks. These are strong atomic lines. And also some diffuse fuzzy stuff, and that is a continuum. And the emission here is called thermal, but it is not black body, as you can see, because there are all these lines. And it comes from plasma, temperatures of close to 1 million to 100 million degrees. And you see most of this emission, between, in the X-ray and extreme ultraviolet ranges. And there are also occasional lines that pop up in the optical and infrared and everything, but the bulk of the emission that I'll be focusing on at least is going to be in the 5 to 200 angstroms range. And what this is called, like I said, it's called the thermal emission. But what it is it's collisionally excited, optically thin, bound, that is line emission, bound free, that's essentially radiative recombination lines, and then free, and that's Bremsstrahlung. Okay. So that's what that's what we expect a spectrum to look like. And this is actually an observed spectrum from a very bright star called Capella. It's an active binary. This over here is a scale model of the system.
literally. I mean, to the best of our knowledge, that is what it would look like if you stood, I don't know, 1 AU from it or something. And what you're seeing up here is a combined something like 500 kilosecond, no, 500, almost a megasecond or more of collected data from the Chandra Observatory with one of the high energy gratings, with a low energy transmission grating. And you can see there's a lot of these lines, and they're marked with occasional identifications, which are not, based on what the plasma might look like at one single temperature. And there are several of them are identified, several of them are not. And the question is, how do we actually understand these things? And to do that, what we have to do is go and look at something called the differential emission measure, or emission measure, or an emission measure distribution. People call it different things. It's the same thing. And to get to that, we have to go through a little bit of math. And let me walk you through that. So first of all, if you have a line, if you have a transition going from an upper level to a lower level, the flux is basically, there's the Einstein coefficient. There is the number of the population in the upper level that's available to do this transition. The volume over which it is that this plasma occupies, that is present in. And then there is a factor that converts this number into an energy, hc over lambda, simple enough. And then a factor that tells you how far it is, just a distance modulus, 1 over 4 pi d squared. I'm mostly going to ignore these things and only focus on this part. So let's say we take this number of sites essentially that you can have where you can have this transition. Multiply and divide by several of these quantities where here n z sub I, z is the atomic number, I is the ionic state, and you have this ratio here, and take, so this basically the number of ions of a particular element, n sub z as a number of number of atoms of that particular element. N sub h is the number of hydrogen atoms in the plasma, and N sub e is the number of free electrons in the plasma. Okay, and let's see if we can do this slightly more in a principal fashion. So we do the same thing for the Einstein coefficient also. So now it's also in terms of per unit volume. And then we can group these things. Oh no, this is going off the page. Oh, this is good. Oh, okay, we're good. Look at this one. So we can group these things and put these things into one slot. I'll tell you what these things mean in a minute. So the first square here, this contains all the atomic information, and that's usually called the emissivity. The next thing is the fraction of the atoms in the particular ionic state, and that is the ionization state. And then the number of atoms of a particular element with respect to hydrogen, that is usually the abundance, the composition. And then this factor NH or NE, which tells you the state of ionization of the plasma, is usually of order 1, and you can mostly ignore it. So, for a fully ionized plasma, it's around 0.84. 10%. We are astronomers. Who gives? Who cares? And then everything else turns into something called n squared delta V, which is actually the crucial part of everything that I'm going to be talking about. So I'm going to take this n squared delta V and convert that into a function of temperature, because it becomes very convenient to deal with things. And since temperature in this case is a nuisance parameter, I can just integrate it out over d log t. It can be dt. This thing here is called the differential emission measure, and that is the one that is really of importance that I'll be that I'm leading up to. So as I said before, the quantity in front is irrelevant. So the flux actually is proportional to whatever the emissivity is times the ionic state times the DEM integrated over the temperature. Why did we have to do it this way? What have you achieved by doing all this very messy algebra? This part is almost entirely atomic physics. This part is almost entirely astronomy. So we've split the problem very nicely into a part where we can leave part of it off to the physicists and then deal with the part that we care and that changes from source to source. So essentially, all we have to do is measure the flux for a large number of transitions. You get a matrix, and you invert the matrix, and you have the DEM, right? So it seems simple. But it is not, and that is what I'll be talking to you about next. So how does it actually work? So let's say you have a temperature, you have a DEM. That's your n squared delta V as a function of log t. It might look like that. This is, for example, this is what the DEM for a solar active region might look like. And what we want to do is get at the flux. Well, let's see, let's consider some cases where you might have a large number of emissivity functions. This would be the product of the emissivity, the ionic state, and the abundance. And you have several such bumps as of over the temperatures and a function for the continuum in green. Okay. Now, what you do is you take this, one of these, this purple emissivity function at this temperature, you put it over the DEM, and then you multiply that together, and you get something, you get a value, right? And that is pretty much what you might get. And of course, the order of this is a function of wavelength, and this order does not necessarily have to be the same as the temperature. It can be scrambled. But as one thing I want you to notice is that the peaks of these flux distributions, each of these lines, do not necessarily match what the emissivity functions have. A lot depends on how much emission measure there is at any given temperature. And even though in some cases you might have a large emissivity, you might still get a weak line. And even if you have a similar size line, you might get a large line flux. Okay. This becomes pretty important because this is the part that really messes things up. Yeah. Sure.
Can you remind me what delta V is?
What?
What delta V is?
Oh, V is the volume. V is the volume.
So 25 on top is volume and function of temperature, so it's not really the derivative of the volume over temperature.
Good point. Yes. 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 So just to make things very confusing, people use the same they use the term differential emission measure to denote something that is n squared dV d log t or n squared dV dt. They use the word emission measure distribution to say n squared dV. And then they use EM as emission measure as summation over volume, so n squared V. So when I say emission measure, I mean all these things. Okay, so don't take the specific form of the thing very seriously. It is just but the important thing is that there's an n squared, and there's a volume and they're usually conditioned on temperature, and some often not. The part that's really that I'm going to be talking about is the one that is conditioned on temperature, but it's and I'm going to consistently use dvd log t, but in the literature you'll find dvdt, you'll find dv, so everything. So keep that in mind. Thank you. Very good question. I was wondering how to explain this sort of complexity. I mean, this is not really a systematic error, other than in terms of how people read and understand these things, and it can lead to systematic errors. As you know, astronomers have problems with units, or at least I have problems with units. So thank you. Right. So what might it look like in real life? So this here is an example of an application of deriving a differential emission measure for solar data. And it is very messy. So this is the solutions nominally go from log t of 5.5 to 7.5 here. These are for two different bright points that were seen on the sun. And the green boxes here are 50% ranges, the quantiles for at the different temperature bands. The red dashed line is the best fit temperature. So you can see that it's there's a and these vertical bars denote the full range of the solutions. And this was derived from an MCMC based solution, so that it goes all over all the way. But a couple of things you can notice: there are two different bright points simultaneously obtained on the sun, but they do produce very different shapes of the DEMs. So this one, for example, has a spike at around 6.4. This one has a spike at around 6.1. So there's a clear difference in how the different parts of the sun might respond. Clearly, there is lower temperature plasma here than here. There is more high temperature plasma that's going off to around 10 million degrees. And these are things that matter to solar physicists or even astrophysicists because they're telling you that there is a process which is producing this high temperature plasma, and typically that's ascribed to flaring, nanoflares, microflares, that sort of thing. So it's a very useful thing to have this differential emission measure. Just by looking at the shapes, you can tell what the physics might be. So it's worth doing. That's the point that I'm trying to get to. But there are problems. So the first thing that you need to know is that the integral that I wrote down, it's called a Fredholm equation of the first kind, which means that there are instabilities at small scales. So back to this plot, and what you can do is, so you have the solution, and you can push this this point up by that much, and this point and the point next to it down, and you get exactly the same number, right? This is not a question of getting a solution that is statistically similar within the uncertainty of the data or anything. You'll get the exact number. You can get that by just moving the values around. So, which means not only is that there are these huge variations that are possible, but also you have degeneracy in the solutions. This is mathematically a very hairy, intractable problem unless you impose some very strong assumptions about smoothing. And that is pretty much usually what people do. People impose different types of smoothing. The mathematicians call it regularization, which, okay, right? You want to capture the essential physics, but sometimes if you do have processes where you do have this sort of bump, you're going to miss that thing if you don't allow for that to happen, right? So solar and coronal physics at this point is in a state where the physics is not so strong that you can make such assumptions. So, keep in mind that your systematics now can include model misspecification that arises during the analysis, right? I mean, you're cutting off large swaths of the physics simply by how you are analyzing the data. Not a good thing. So keep that in mind, right? Okay, and of course, if you have several points in solution space that map to the same point in data space, that's a many-to-one degeneracy. And on top of that, you also have a very large dynamic range in the problem. So you can have a DEM that is very high at one point and very low at another point, but emissivities that do the reverse, and you get similar fluxes, even though you're getting lines from very different temperatures. And on top of that, the densities can vary from 10 to the 8 to 10 to the 12, 4 orders of magnitude. N squared then makes it 8 orders of magnitude. Volume can go from less than 10 to the 23, as far as we can tell, to greater than 10 to the 30, more on stars, positive, some stars. So that's 7 orders of magnitude at least. So 7 plus 8, 15 orders of magnitude already. So you show me one statistician who can deal with 15 orders of magnitude, and I'll say, no, there are no such people. Okay, statisticians just don't get that there is that we have to deal with these dynamic ranges. I remember that that there was this one problem where we were dealing with, we were suggesting there could be factors of 10 variations, but for statisticians factors of 2 is large. Okay, so keep this in mind again when you look at solutions. This might be something that's something to care about. So the same thing, showing you the highlighting the range in this emission measure distribution. It goes from 10 to the 23 to around 10 to the 30. So okay, the next thing to note is that it depends on density and volume. They're both functions of temperature. So here, for example, is actually this is what the sun looks like now, or yesterday. And if you zoom into a part of it, you can see loop-like structures, right? You can see these loops going off all over the place. And if you have a look at a model of what these loops look like, what happens? This is a lucky thing, and this is by no means a necessary thing. Most of the bulk of the loop is at a single temperature and a single or very, very small range of temperature and density. Completely coincidentally, completely luckily, because that means that we can, ignore most of the various strong variations in the density and volume and just treat it as some sort of a combination. And even further, we can pull the density out and just look at the variations of the volume and temperature. But this is a major assumption in how people deal with the DEMs and deal with the analysis of interpretation of the spectra. I just wanted to highlight that and keep that in mind. Oh, and also the other thing is that, as I mentioned earlier, this is collisionally excited, optically thin, which means that you can ignore things like opacity effect. Everything is transparent. So you see something that's apparently close to the surface of the sun, you see that all the way through, and there's nothing blocking it. Except in some cases where you do need to worry about that in some strong absorption lines are present, and those need to be handled individually. But on the whole, by and large, it's not a big deal. Okay. And then you saw a little bit of this in the GRB talk by John, and even the measurement of what you call a line is subject to systematics, because what a line might mean is in a sense interpretable, right? And I don't mean that in a nice context. So you know that a spectrum is made up of lines and continuum. And let's say this green thing is the continuum, the blue is what you actually see, and there might be a bump here, which could, in principle, be made up of multiple lines. If you don't know a priori that there are two lines here, you're going to try to fit it with one line, and you're going to get a completely wrong estimate of, I don't know, the Doppler velocity, the thermal velocity of the plasma, or or there might be flows in the line. All these things are going to go wrong, right? The good news, though, is that there have been over the past, I don't know, 2-3 decades or so, people have been building up a very complex database of atomic lines, and they are very, very complete down to the detectability limits of most instruments. And we're very confident that at least all the strong lines, we know what is happening around them. Up to around 10% or so. So, if your result depends, is good to around 10%, you're probably okay. But there are still faint lines which are missing, and these faint lines get stuck into the continuum. And when they do, then you estimate the level of the continuum. And how do you get abundances? By looking at the ratio of the line flux to the continuum flux. And if you don't know what your continuum is properly, to within 10%, your abundances are off by that same amount. Okay. So, which means also that the way that this is one of the reasons why you have to, with all these problems, you have to get the DEM, because the DEM then lets you predict the continuum there should be. So you know what, there's plasma at this temperature, you know what the continuum should be, because otherwise it's very difficult to find the continuum. You can find the lines much more easily than the continuum. Another reason to actually do this problem, even though it is a pain. All right, and finally, now we get to the talk that I was supposed to give. Atomic data uncertainties can cause highly nonlinear effects on both the emissivity and the ion balance, okay? So we have this expression for the flux. There's abundance, the emissivity, ion balance, and the DEM. Let's look at what might happen. So this blue curve is the, let's say, the emissivity. And these purple, red, and orange curves are the ion balances. Now you can get these variations for a single species, both because you don't know what the true ion balance is, which is possible, and also because the system is not cooperating with you. In most cases, you get an ionization balance curve, which tells you how much of the ion is present at what temperature, and where you might see most of the ions occur. For example, if you have highly, you need higher temperature for more ionization. So if you want a hydrogen-like ion of oxygen, for example, oxygen 8, you want the temperature to be way high, right? So, but then how do you get to that temperature? You have to have a sudden release in energy. You need to have a flare, which means that there's a dynamic process going on. And when there is a dynamic process going on, which means it's not stationary, the plasma is changing, and you might actually get more of the lower ionization states pop up, even though the apparent temperature is lower. or if there is continuous injection of energy into something, then you can see the ion showing up at apparently higher temperatures more than it ought to. So you can have these deviations happen simply because the plasma is being, doing its own thing, and your assumptions about the physics are broken. What people usually do is, at least in the case of the sun, the observations occur on a cadence where this dynamic evolution is less of an issue. So over several over a minute or so, everything has equilibrated enough that you can continue to use a single ionization balance. But that, of course, still doesn't remove the problem of uncertainties in the ionization balance itself. That is still something we need to worry about. And you could have the same problem with the emissivities also. Remember that I wrote it down as Einstein coefficients times the number of elements in the number of atoms at the upper level. These are all subject to strong uncertainty. Even the Einstein coefficient needs to be calculated because it's not known or measured for almost all the lines that we're interested in. So your emissivity function, instead of being this blue thing in the middle, could be shifted up or down. And this is something that needs to be taken care of. Here, for example, is one way that people use these data. What you're seeing here is a level diagram of a helium-like triplet system. This is, there are three big lines that you usually see, and you can see those lines over there in several different stars. And you can see that they don't all have the same relative intensities. And the reason for that is that the way how these are arranged. So this one, also labeled W, is a resonance line, which is pretty stable. And then there is a metastable state here, which lets you come down through this alternate pathway and produce two different lines. One is an intercombination line that goes down to ground, and then there's a forbidden line. Of course, when you say forbidden, it just means that it is forbidden under first order approximations of the shell model. There is still overlap that gives you a small probability that this transition can still happen. And what happens is that as you go, as you change the density of the plasma, the relative the intensities of these two change, because more stuff gets populated here when the density is higher. So you can you can look at the ratio of the forbidden and intercombination to the resonance, and that'll give you a sense of what the temperature might be of the plasma. And you can look at just the ratio of the forbidden to intercombination, and that'll tell you what the density might be in the plasma. And what might happen if you don't know this exactly? So people have tried to see the effects of this. This is, by the way, just want to point out that these three, this is reversed. This is actually 10%. This is 30%. Typo in the paper. Can't do anything about it. But anyway, so so this is the G ratio that I pointed out to you like this. This is what it might look like. Oh, I forgot to mention one very important thing. So there are different curves here. And these curves are including different numbers of levels in the atomic calculation. So if you do a more thorough calculation, let's say you include 10, you get this solid curve. if you limit yourself to just the two most important levels, let's say 1 and 2, you get this curve. So you can make a huge error if you don't go far enough into the calculation. And these can be really, sometimes there can be thousands and thousands of levels and you're trying to solve a complex quantum state with 1,000 by 1,000 matrix or worse. So keep in mind that just these calculations are supercomputer worthy. And just because we have a number does not mean that we know what it is. Okay, so anyway, so yes, so if you assume that if you impose a 10% or a 20% or a 30% uncertainty on these, what might the on the collision strengths, individual collision strengths, these tell you what kind of variation you might see. So at 20%, this slightly shaded region, what you might have thought was the right temperature here is now actually that range. Okay, so it can make a huge difference. All right. How much time do I have? Oh, okay. Perfect. I'll finish rapidly. So David Van Dyke actually was, and I was involved in this work. So we decided, okay, let's try something more sophisticated about how to do this density estimates, for example. This is, that thing is covered up. It's supposed to say iron 13. So there's a system of lines in that is mostly where the intensity ratio of the intensities between them are not temperature sensitive, but they are density sensitive. And we looked at the sun, where we can see mostly the lower parts of the loops. And in this case, the emission is going to be dominated by parts where the density is high. So remember what I said about approximating the density and the temperature by small ranges? In this case, we are not seeing the loops. We are seeing only the foot points of the loops. So here, for example, is a regular UV image. You can see all these loops, and an X-ray image, again, all these loops. And this rectangle is showing you the ion emission in the same regions. And mostly what you can see is just the base of the loops. So what you're doing here then is trying to estimate the density properly, taking into account the uncertainties that might exist in the atomic physics. And here's one way that you can do this. I mentioned to you before that I told you that several if you take into account different levels, different ways of calculating things, you get different results. So you can do this. You can compare the result of what one group gets versus another group, and look at what kind of variation they might see in their estimates of the collision strengths or the Einstein coefficients or any of these things. And once you have that, I mean, that tells you that there is at least this much uncertainty in your calculations, right? So this is not the whole thing, but this is going to, going to at least, a large fraction of accounting for these things. And you can kind of see this dashed line over here. That is, that's like a smooth, not a fit, chi by I sort of trend line, which you can use to say that, okay, there is more uncertainty when the collision strength is low, less uncertainty when the collision strength is high, and take that into account and do simulated emissivities and then see how it might work. And we use this pragmatic Bayes and the fully Bayes methods that David mentioned earlier today. And these are, for example, the results that we get for the different emissivity curves for iron-13 from this analysis. In this, the red is the original value. The gray shade is the range of different, the range that we get from the uncertainties. And the green is the best fit, or the value that we get from the fully Bayes analysis. Okay. Okay. And here's an example of that specific thing, how this works. So this shows you, this is a contour plot of density versus, in this case, we're just using path length and not volume, but you just need to multiply it by a constant area and you get the volume. And what you see as the blue is what you would get without, including any of the atomic errors. The red is what you would get from the pragmatic Bayesian, which is, allowing for the various, for all possible variations in the emissivity to be true. And then the green is the part where you eliminate the parts which are less consistent with the data and keep only the part that makes sense. And you can see that, okay, that did shift. So, it's working as expected. All right, so, and then we did one more thing, which is, so the previous one was we're using extracting just the density. And then we did one more step, which is to include a single temperature in the DEM. So this is still not the full DEM. We're still working towards it. But this is applied to the accumulated Chandra data. When you saw that movie go by earlier. And the idea is to get the estimate of the temperature from 13 lines of the density insensitive iron-17 line, and then use that as an informative prior in estimating the density and the temperature using only 6 lines of oxygen-7. And here we made a slight improvement. We started handling the atomic emissivity uncertainties, also obtained in a similar way as before, using principal components as an answer, because that lets you fill in gaps in the emissivity functions, which was another mathematical thing that we have to worry about. This is just to show that the fits worked. This is the original spectrum with everything other than the iron lines removed, the iron-17 lines removed, and the same thing with everything other than the oxygen-7 lines removed. And this is the gaps removed from that. Same thing here, and these are the residuals of the fit. It seems okay. This is ±2 sigma. There are a couple of excursions, but then, as I said, several megaseconds of data, you expect to see variations, okay? And this is what the temperature distribution looks like from the iron-17 analysis. This is the pragmatic Bayes, and the fully Bayes pulls it almost entirely off into the tail. And similarly for the volume. But this is not the final result. This is the real final result. This is the temperature after including the oxygen-7 data, and here the pragmatic and the fully Bayes are much more closer to each other. Probably partly because we are using a very highly informative prior to get to this point at this point. And also, this is for the density, which again, pragmatic Bayes gives you large deviations, large wings, and the fully Bayes gives you a very narrow estimate. Okay. And one other final source of systematics that we have to worry about is calibration. So the spectrum movie that you saw was for the LETG HRC, which is just one of the instruments on Chandra. There are the ASIS LETG, that's the ALP and the ALN, and the ASIS HETG and the HEG and the MEG, which is the AMP and the AMN here. So this is the first run as first stage log temperature, second stage temperature, closer, but still there's variation, and it's of the order of the calibration uncertainties that we expect. Okay. All right. I will stop here and just point out to you that there are several issues that need to be that you need to worry about, and they are of different ilk. You know, there's a mathematical issues, there are observational issues, modeling, astrophysical assumptions, and finally atomic data. So this is, you know, this is such a huge problem that several people will just throw up their hands and just say, oh, okay, nothing that we get from any of this analysis is of any use. We will not do it anymore. I think that is a misguided notion, mostly because even with all these, we can still get to a part of the parameter space where we have confidence that it is reasonable. So it is worth dealing with the systematics. We have to at least understand what the systematics are, because the DEM by itself is actually pretty useful, and it is worth the trouble to make sure that we get it right. All right, thank you.
Yes, please. Yeah.
Thank you for the talk. So can you go back to the initial equation where you actually split the ionization fraction, the emission parameter, and also the the emission measure? That I still remember my the Saha equation, right?
This one?
So I feel like in the Saha equation, the ionization ratio of the two different adjacent states depends actually on also not only temperature but also the electron density.
Yes. Yes.
So I wonder why the NE is not combined with the third term in this equation at the bottom.
You mean
instead actually in the first in the third one?
this thing?
No, I mean the next one.
This one?
So that is from Saha equation, right?
At this point, it is just, why is it, what is moving? Oh.
Yeah, right.
At this point, it is just algebra.
I know.
So,
but you explicitly created a new term of electron density and put it into emissivity term.
oh, here, yes.
Yeah.
Yeah, yeah.
So, but clearly the ionization fraction also depends on electron density.
Yes, it does. Yeah,
so-
it does. This is where the luck that I was telling you about comes in. So the fact that in most of the cases where we actually apply it, we can we can assume that the density is mostly fixed. Solving it for the general problem has been so far very difficult.
So sorry, that was the plot that you showed that almost constant density for
Yes.
temperature. So
Yes.
that's an assumption.
It is an assumption, yes.
Yeah,
It
but
is
then-
absolutely an assumption, and it should be kept in mind when and doing the analysis of interpreting any of these things, yes.
Okay, so when you are calculating the ionization fraction, when you are for each individual species,
Yeah.
you are holding the electron density as constant.
We are estimating everything under the assumption that the density can be factored out. There is only one density that controls most of the emission. And so so that thing that I mentioned about the temperature being mostly flat across the loop, that helps. And the second thing that helps is that the emission, the flux is dependent on n squared. So the most of the counts, most of the flux that you're seeing is luckily or thankfully or coincidentally coming from parts where the density is highest. So that is why, when you look at images of the solar corona, you see striations of these loop-like structures. These loops are really just plasma filling a flux tube, but the flux tubes are space filling. So the only reason you can see these lines is because there is an increase in the density and along those lines. So what we are looking at is parts of the corona where the density has been enhanced, and parts where the density is low, we don't get the data from. So it's a as I said, it's a lucky coincidence, which doesn't always hold, and you got to be careful when you look at a particular data set when it doesn't hold.
Yeah, what a nuisance physics is for
Physics, yes.
right? Just
Yeah.
completely
I mean,
annoying.
it's
Maybe one more question. We are a few minutes late, but that's okay. We have a long break for lunch. Anybody? No? I suppose, yes.
I'm actually gonna ask you this number, but I found your talk really fascinating. But I still don't quite understand. So what is the bigger picture of actually measuring the density at the base of the loop and the temperature of the loop? What the
so the
impacting?
Yeah, the stuff that I talked about here. Yeah, the stuff that I talked about here was mostly as an astrostatistics exercise to take what we can figure out about the uncertainty in the atomic physics and see what it might tell us about the density estimation. And what you saw here was clearly that it does shift things. But it goes from what was it? Density of 9.7 to 9.6, so factor of 2, right? So it can be important to estimates of where. So what we're looking at here are what's called the moss or the foot points of the loops, and these are actually fairly dynamic, quite dynamic systems. I mean, there is plasma coming up, there is flow out of the chromosphere, and there are several models, hydrodynamic models that try to figure out how these things work. Are they doing a good enough job to do that? That is, if we have a good handle on the density estimates and the corresponding length scales that are involved, then we can go back and look at those things, those physics models, and see how well they're doing. So which one is, yeah, so not this. Which somewhere here, oh yeah, this one. This comes from a hydrodynamic model, which has been applied not only to the sun, but even to flares on stars. And it's unclear how good it is. So, the more we can help constrain these things, the better. Right. Yeah.
All right, thanks so much.
Thank you.
We'll wrap up the morning with Jeroen. Is that
Yeah, that's perfect.
Okay. In space science, yes.
It's on the bottom, I think. Ah, here. Yeah, perfect. Hello, good morning, everybody. So my name is Jeroen, and I'm a research scientist at MIT working on machine learning for the NASA Transiting Exoplanet Survey Satellite, or the TESS mission. Now, TESS is a, let me see how I'm slides. Ah, perfect, thanks. Yeah, so TESS was launched in 2018. It's a NASA survey being led by MIT. As you can see, it surveys the full sky, and it does this most of the time in sectors of 27 days at a time. Currently, actually we're taking observation for up to 54 days at a time. And we take an image of the sky every 200 seconds in that. After 27 days, what we do is we shift to the next field of view, and then we cover about half the sky in around 1 year. So we've been observing since 2018, and we have lots and lots of data so far. And what you can see here, this is one image of what TESS is taking. So TESS consists of 4 cameras, and each of those cameras has 4 detectors. And of course, uncertainty is actually, so depending on where exactly your pixels fall that you're interested in, the sensitivity is slightly different. So this can actually result in uncertainties in the type of data that we're extracting for that. Now, as you can see, this image is of part of the sky, so taken at one point in time, and it consists of millions and millions of stars. It's around between, I would say, 2 to 10 million stars, depending on how faint in magnitude you go down to. Now, if we want to process that data, what we do is we actually zoom all the way in. So you find each individual star in there, and you extract a brightness measurement. So let's say we find a star, you see a couple of pixels, so that's just one star, as you can see over here. Then the question is, of course, like, how do we define such an aperture mask? So this is just for one point in time. Do we make it circular? Do we make it square? Do we make it a little bit more non-symmetric? And depending on what you do, this can actually already introduce some kind of errors here already. Some of the pixels might not exactly fall in that same part. So you might lose a little bit of information, or you might capture pixels where light from nearby stars falls on there. So what you'll get in that case is actually some contamination from other stars, and you might not actually be picking up this as a signal you're interested in. Now, what you do if you do that at each point in time, so we have every 200 seconds, we get a brightness measurement. Then over time, you get a light curve. I think we saw some of these things before already as well, but you get the brightness over time. And the main goal of TESS was to search for exoplanets, so planets outside of the solar system. But you can also use for a lot of other different science cases. One of them, for example, being astroseismology, which are a study of star quakes, similar to earthquakes, so stellar oscillations essentially. What I'm showing here is the light curve of an eclipsing binary system. So 2 stars orbiting a common center of mass. And you can see here, these are the dips that are being caused by that. Now, as I said before, there's a lot of ways that actually systematic effects and uncertainties have an effect on our final data product. So this light curve is what we mostly use in astronomy to work with. But these are extracted from the raw images, right? So if you have your raw image, there's multiple ways that it can affect them. The top one is, for example, we have observational effects that can hit our detectors. So you have light from the sun that's reflecting off the Earth and the moon, and then you get this nice glare actually over there. But now, if I'm interested in this particular star, and this is this whole glare of scattered light, we call it, then this obviously affects our measurements on the image. So if we're looking at a time series, we actually see something like this. You see these sudden rises, and that have a very big effect on our final analysis. But we can actually correct for that as long as the detector doesn't saturate. And Daniel Mutakrishna will talk about a lot of this more, how exactly we do some scattered light modeling tomorrow as well, or which possible techniques you could potentially use for that. Now, other things that I said before is crowding. So if you have multiple stars that fall on the same aperture mass, so you see here, all these black dots are all different types of stars. And the size actually measures the brightness, so the magnitude of the star. As you can see here, if we would be extracting an aperture mask here of this particular star where the cross is, but you see there's other light from other stars falling on those same pixels, well, we'd actually not get a proper light curve, and it's contaminated. So meaning if we would have maybe 2 types of eclipsing binary systems, they might actually mimic a transiting planet. So we might think we're detecting a planet, but in reality, it's actually just a mixture of different types of stars. So there are a couple of methodologies how you can actually take this into account by zooming in on the individual pixels and making light curve per pixel, but it's definitely not yet. They're not completely set yet, I would say. And then if you combine it with more detailed surveys, so TESS has pretty large pixel sizes, but if you have smaller pixel sizes, that's one way to resolve it already, of course. Now, so what we're observing is either on the image level or on the signal level is always essentially a combination of systematic effects that we're seeing. This can be scattered light, where you can see a sudden rise. So if you look at if you would model it as a linear trend, you could have the systematic effects plus your target. I don't think the colors are very well visible here. And this can be either on the image level or on the time series level. So it's always a combination of how we're measuring and what we're measuring, essentially. Now, the idea is that we actually try to disentangle these, of course, when we're doing our final analysis. Now, specifically, what we do is we use a lot of machine learning algorithms to actually process all our data. So one of these things we have, for example, we have data reduction pipelines to find all the incoming, to search all the incoming data for transiting planets. We have the same for stellar variability classification. So we train a lot of different machine learning models for this. And essentially, what you do traditionally, if you train a supervised machine learning model, you have your light curve as input. You take some deep learning algorithm, can be a fully connected network, can be a transformer or anything. And then you predict, for example, the variability class. So whether it's an eclipsing binary, a pulsating star, or something else, or maybe you're interested in some type of style parameter. Here I'm showing you the example of a pulsating star, and that's what you kind of train on. Now you also have something called self-supervised learning, where you can actually train your machine learning algorithm irrespective of any final task. So this actually leads us to foundation models like ChatGPT, for example, where you train an underlying model irrespective of the task that we want to do. So it doesn't matter whether I want to find pulsating stars, just do classification, or actually want to determine their parameters. I can use this representation to afterwards fine-tune it for particular tasks. So I just want to find a very nice representation to actually capture all the properties irrespective of the final task. So you kind of wanted to capture the physics. Now, if you don't take instrument into account and you take that hidden layer, so if you take one of these layers, for example, layer 2, and you put it in 2D, you train a model of images, for example, what you would see is actually that part of this latent space. So here this is all physics, but then if you look at part of the latent space, a lot of the instrument characteristics are actually contained in that. Now, if we then add more observations, this can be problematic because not all of our observations will actually have instrument. But then if for the same target, we have some systematic effects, and we merge those two types of observations, then we'd obviously be biasing our data here or our final analysis. Now, one nice thing about tests and in general about surveys is that these instrumental properties are not stationary, so they vary over time. So tests in sector 14, for example, if you look at the same star observed in sector 14, and then you look at again in sector 15, so 2 different points in time, consecutive, so the first 27 days and 27 days after, you actually see that these systematic effects vary a lot. So it's exactly the same star, but just falling on a different part of the detector. You have slightly different observing conditions, and you see that those trends are quite different. And then if you have that same star observed, for example, by a previous mission, the NASA Kepler mission, it looks even more different. It looks much cleaner because this one had smaller pixels. It was a little bit less noisy. We can actually leverage these overlapping observations. If you take a look at tests, these are the number of overlapping observations we have since we started. So it's a lot of them. So we are always observing the same star, but under different conditions, essentially. And we want to do this, we want to leverage this in our machine learning architectures. Because if you train a machine learning model, as I said before, with just one encoder and you don't take into account specifically the systematic effects. So if you would be doing something like this, you train a machine learning algorithm on different types of time series. You essentially assume that everything you observe is physics. But in reality, this is definitely not the case. What we have here is we have systematics plus instrument, as I was showing you guys in our previous example. So what you can do is actually train a machine learning algorithm, but specifically account for the physics and the instrument components as well. So What you have then is you have two separate latent spaces. One latent space where you assume everything is physics, and one where you actually put all the instrumental characteristics of your observations together. So if the way you can do this is with a technique, for example, called contrastive learning. It's a way where you can actually learn representations by actually combining similar data types or similar targets. And specifically what we do here is we feed the algorithm a light curve here, as you can see here, of the original star. So let's say we take a star number 99 observed in test sector 41. And then we take that same star, but observed in a different sector, test sector 50. And we tell the machine learning algorithm that these two should actually be put closely together in the latent space. And we do this for lots and lots of different stars. And in that way, we force those two to actually be together and be closely together in your physics space with contrastive learning. And then for the instrument space, what we do there is we tell the algorithm, okay, we take any random star observed in that same sector, because we can assume that some of the observational characteristics are pretty similar there. Now, in reality, it's not just the same sector, so not just a point in time, but you actually want to go down to, okay, which camera was it observed in, which detector was it observed in, and then specifically which region of your CCD was it on. Because depending on where exactly on your CCD the light of the star falls, you will have different observational characteristics. The pixels might be slightly different, so there will be some changes over there. And if you can go all the way down to this, you can build it in a hierarchical way, essentially. Ultimately, you also want to have a possibility to add data from previous NASA missions so that you can build some hierarchies, for example, between Kepler tests, and you build all of that into account, essentially. And then in that way, you're actually able to build a physics space and an instrument space. And what you can do is take this physics space, it's trained irrespective of the final task, but you can use it for stellar parameter inference, classification, so different type of stellar variability classes, and for example, anomaly detection as well. Now, if you train your algorithm in this way, we validated for now on lots of different types of simulated data and are running it and did a couple of test runs or actual test data as well. What you see is if you want to predict a stellar parameter, for example, and you compare this to a traditional machine learning model, either a foundation model that was trained irrespective of the final task, or just a simple multi-layer perceptron, so a simple fully connected network that was trained in a supervised way to predict this parameter, we see that if we only provide our machine learning algorithm 10 labels, we actually already get on the order of 65-70% accuracy, or R square in this case. So it's much higher than any of the other ones. So our model with the physics and the instrument space is the red curve, and you see it always outperforms the other algorithms we tested, specifically because we're able to remove part of these systematic effects here. This is quite nice. You can actually dive into the latent space as well. If you want to see, for example, I can show one slide maybe on that part. But if you actually get this physics space and your instrument space, this is what a very simple set of simulations. But on the left, you see your latent space, the physics space that I showed before, reduced to 2 dimensions. And you color code it according to the instrument number. You see there's no correlation at all. But if you color code according to the period of your light curve, you see there's a nice correlation, same with the amplitude. Now, if you take the instrument space and you color code that according to the instrument, you see, there's a nice correlation there as well. But if you color code according to the period or the amplitude, you don't specifically see that correlation. This was a very simple set of simulations. If we do it for more complicated ones, we see still a little bit of leakage, so it's not completely separated. So here you see the same space, you see the stellar space, the instrument space. If you color code stellar according to instrument, not a lot of correlation. But if you then do the same thing in the instrument space, you do see the correlation. It's not as nice separate as before because we have more complicated models. But then if you take here, you color code both of the space according to the stellar parameter, you see that there's a little bit of leakage here still that's happening. But there are some ways where we can actually solve this. One of them, if we transform the model into a generative one, that might address some of these limitations. And Daniel will talk a little bit about this more as well. So we're working actually solving this leakage and to get even better predictions. And what you then do here is, you take that stellar space and then you can use it to build, to have better downstream accuracy on your specific task that you're trying to deal with. So I think I'm about to run out of time, so I'll stop here. But yeah, happy to answer any questions. So you mean for estimating so for specifically calculating the period itself? Yeah, so I haven't specifically checked what it does for like period determination, what the difference is there. What we did do is for specifically if you want to predict the stellar parameter, so that's an exact test that we run. Like if you want to predict your stellar parameter, then we see depending on how many labels you have. So this is the red curve essentially, right? So on average, you see 0.7 on the first case to 0.4 essentially. In our square, so that's the difference. I did not specifically test it for a period, but essentially this is a similar one. Yeah, exactly. I think actually this one, now that this is for a set of simulations, and it's actually based on some kind of Fourier series related to the frequency. So it's in that way, it's a little bit similar. Yeah.
So you mentioned crowding. Can you elaborate a little more on what that is?
Yeah. So if you have, yeah, so one of the ways what people do is here is you build light curves on a pixel level basis. So usually you select multiple pixels and then you use that to generate your light curve. Now you can also generate light curves on each and just you take each pixel and then you build a light curve for each single pixel. And then you can actually see how that one changes too. And then you could look at some, I think there was a method where they look in the different power excesses in each of those pixels to try to then kind of disentangle that too. There was actually a case where they thought they found a new type of pulsating star, but in reality it was just a crowding that happened. And then if you analyze it in very much detail, you can actually see that there were separate stars. And then the other one is you add information from Gaia, for example, which is a space mission as well. Now you know exactly where everything falls. So then you have a way to better represent where other stars are, and then you can kind of account for that too.
Just to add to that, in lattice surveys, you also have like probability interlopers. Did you at all account for that? Is that a probability here at all?
Could you repeat the first part?
In lattice surveys, you also have to account for interlopers like galaxies. Basically, foreground versus background galaxies and so on. You account for that.
Yeah, so that's one thing. I think it's a little bit related to crowding as well, where you have the foreground and the background. So I think it's similar, and it depends. Like usually we do this on a more detailed level analysis. So on a high level, we just generate all the light curves, we extract them. And then if we're interested in a particular star that seems very interesting or a particular light curve, then we start looking at it on an individual basis and trying to actually validate whether it is background on there or not. And then usually we add information from other space surveys as well, especially ones that have finer pixel grids, because TESS has very large pixel. This is more problematic than if you would take a ground-based survey, for example.
More questions? It's like everybody's ready for lunch.
Perfect.
Okay, thank you so much. And as I said, about be heading, towards the cafeteria, so probably Stephen too. So just follow me if you